Picture a world where the sky glows in shades of butterscotch and salmon pink, where dust devils dance across ancient riverbeds, and towering mountains hold secrets buried for billions of years. This is Mars, our neighboring world, and somewhere on its rusty surface, a car-sized robot is slowly climbing a mountain, reading the story of an entire planet written in stone. Welcome to the story of Curiosity, a rover unlike any that came before it. For over 13 years now, this remarkable machine has been exploring Gale Crater, a vast depression that once held a lake larger than any body of water on Earth today. Every drill hole, every laser zap, every photograph tells us something new about whether Mars could have once supported life. When you look up at Mars in the night sky, that tiny red dot, it's easy to forget that right now, at this very moment, Curiosity is there. It's analyzing rocks, measuring radiation, sniffing the thin atmosphere for traces of methane. It's alone on another world, but it's not lonely. Back here on Earth, teams of scientists wake up each day to explore Mars through its mechanical eyes. This isn't just a story about a rover. It's a detective story spanning 4.5 billion years. It's about water that flowed when Earth's own oceans were just forming. It's about mountains that rose from lake beds and atmospheres that vanished into space. It's about the question that drives us to explore: could life have emerged on Mars the same way it did here? The Curiosity rover launched from Cape Canaveral on November 26, 2011, but its journey really began decades earlier, when scientists first started dreaming of a mobile laboratory that could truly investigate whether Mars had ever been habitable. Previous rovers had found tantalizing hints, but Curiosity was designed to go further, to drill deeper, to answer bigger questions. Its destination was carefully chosen. Gale Crater, a 154-kilometer wide impact basin near the Martian equator, offered something no other landing site could provide: a mountain made of layered sediments rising 5.5 kilometers from the crater floor. Scientists named it Mount Sharp, though officially it's known as Aeolus Mons, and those layers represent a geological record stretching back billions of years. If you wanted to read the history of water on Mars, this was the library you'd visit. But first, Curiosity had to get there. And that journey would prove to be one of the most audacious engineering feats in the history of space exploration. The spacecraft carrying Curiosity covered over 567 million kilometers during its cruise to Mars. For 8.5 months, it traveled through the void, a metallic cocoon protecting its precious cargo. Inside, Curiosity waited, powered down, dormant, while its systems were periodically checked by the mission team back home. Space travel isn't like driving down a highway. You can't steer much once you're launched. The trajectory was calculated with extraordinary precision, threading a needle across interplanetary distances. Small course corrections were made along the way, tiny thruster burns that nudged the spacecraft onto the perfect path. Miss by even a small margin, and Curiosity would sail past Mars entirely, lost forever in the solar system. As the red planet grew larger in the spacecraft's view, engineers back at NASA's Jet Propulsion Laboratory in California prepared for the most nerve-wracking part of the mission. They called it the 7 minutes of terror, and for good reason. From the moment Curiosity's spacecraft hit the top of the Martian atmosphere to the moment its wheels touched the ground would be 7 minutes of automated chaos. Radio signals take 14 minutes to travel from Mars to Earth, which meant that by the time Mission Control saw Curiosity enter the atmosphere, it would already be on the surface, either safely or in pieces. The rover had to land itself. August 5, 2012. The entry, descent, and landing sequence began the moment the spacecraft slammed into Mars's thin atmosphere at 21,000 kilometers per hour. The heat shield protecting Curiosity's underside immediately began to glow, reaching temperatures of 1600 degrees Celsius as atmospheric friction stripped away the spacecraft's enormous velocity. For 4 minutes, Curiosity plummeted through the Martian sky, wrapped in a cocoon of superheated plasma that blocked all communications. This was the blackout period, when mission controllers could only wait and hope that everything was working as designed. Inside that fireball was $2.5 billion worth of scientific equipment and a decade of work by thousands of people. As the spacecraft slowed to about 1,600 kilometers per hour, still 11 kilometers above the surface, the parachute deployed. It was the largest supersonic parachute ever built, nearly 21 meters in diameter, and it had to work perfectly on the first try. There would be no second chances. The parachute slowed Curiosity to about 320 kilometers per hour, still far too fast for a safe landing. 20 seconds later, the heat shield separated and fell away. For the first time, Curiosity's radar could see the ground rushing up toward it. The rover's computer compared what it saw with maps loaded into its memory, figuring out exactly where it was and where it was going. This was technology that had never been tested on Mars before. If the radar failed, if the computer made a mistake, if the maps were wrong, Curiosity would crash. At 1,700 meters above the surface, still traveling at nearly 300 kilometers per hour, the backshell and parachute separated. For a brief, terrifying moment, Curiosity was in free fall. Then the Sky Crane fired its rockets. The Sky Crane was perhaps the most audacious part of the whole landing system. Previous rovers had used airbags to bounce to a stop, but Curiosity was too heavy for that approach. Instead, engineers designed a rocket-powered platform that would hover above the ground while lowering the rover on cables. It had never been done before. Many people thought it was too risky, too complicated. But the team believed in it. The 8 rockets on the Sky Crane, each capable of producing 800 newtons of thrust, roared to life. They had to counteract Mars's gravity while also cancelling out all horizontal motion. The rocket platform had to come to a complete stop in the air, hovering steady as a helicopter, before it could lower Curiosity. The rockets gimbaled and throttled, responding hundreds of times per second to keep everything stable. At 20 meters above the Martian surface, the Sky Crane began to lower Curiosity on 3 cables, each 7.5 meters long. The rover's wheels deployed, spreading out into their landing configuration. The rover descended at 3/4 of a meter per second, a controlled, gentle lowering toward the ancient rocks below. When Curiosity's wheels touched the surface and took the rover's full weight, the rover knew it. It immediately cut the cables. The Sky Crane, its job complete, flew away and crashed intentionally about 650 meters from the landing site. Its final act was to take itself out of the picture, ensuring it wouldn't contaminate the area Curiosity would explore. Mission control erupted in cheers. Curiosity had landed, right on target, in the smooth plains near the base of Mount Sharp. The 7 minutes of terror were over. Now the mission could truly begin. That landing site, officially known as Bradbury Landing after the science fiction author Ray Bradbury, who had passed away just weeks before, would be Curiosity's home base for the first days of the mission. But the landing spot wasn't chosen randomly. Every square meter of Gale Crater had been scrutinized using orbital imagery and decades of Mars research. Gale Crater itself is ancient, formed by a massive asteroid impact somewhere between 3.8 and 3.6 billion years ago. Picture the moment of impact, a mountain-sized rock screaming through the Martian atmosphere, hitting the surface with the force of millions of nuclear bombs. The explosion would have vaporized the impactor instantly, blasting a hole tens of kilometers deep into the crust. The shockwave would have traveled through the planet's interior. Rock melted and flowed like water. A curtain of debris arched up and fell back, creating the crater rim that still exists today. But Gale Crater's story didn't end with its violent birth. What happened afterward is what makes it so special. While Mars was still relatively young, while it still had a thicker atmosphere and liquid water on its surface, Gale Crater began to fill. Not with water initially, although that would come later, but with sediments. For perhaps 2 billion years, layer after layer of sediment accumulated on the crater floor. Some of these layers were deposited by water, either in lakes or by rivers flowing into the crater from the highlands to the south. Other layers were laid down by wind, as Martian dust storms heaped fine particles into ever-growing piles. Still other layers might have been volcanic ash, the remnants of eruptions from the massive Tharsis volcanoes hundreds of kilometers away. The crater filled and filled, perhaps completely, burying any trace of the original impact basin under kilometers of sediment. And then, something changed. Mars began to lose its atmosphere. The planet's magnetic field, which had protected the air from being stripped away by the solar wind, weakened and failed. Without that shield, the Sun's charged particles began stealing Mars's atmosphere, molecule by molecule, over millions of years. As the atmosphere thinned, liquid water could no longer exist on the surface. The climate dried. Lakes evaporated. Rivers ceased to flow. And the winds, no longer competing with rain and running water, began to dominate the landscape. Those winds eroded the sediments that had filled Gale Crater. Billions of years of patient, grinding work removed most of what had accumulated, carrying it away particle by particle. But erosion isn't uniform. Some materials are harder than others. Some areas are sheltered from the wind. And so, as the crater was slowly emptied, a mountain was revealed. Not a mountain that had risen from below, but a mountain that remained when everything around it was worn away. This is Mount Sharp, and its very existence is a monument to the power of time and erosion. The mountain is made entirely of sedimentary layers, each one representing a different era in Martian history. The lowest layers, the ones Curiosity would eventually reach, were deposited when Mars was wet and potentially habitable. The upper layers, high above where Curiosity would ever climb, were laid down when Mars was already dry and cold. Imagine being able to read a history book where each page is a layer of rock, where you can trace the transition from a warm, wet world to the frozen desert Mars is today. That's what Mount Sharp offers. That's why scientists chose Gale Crater for Curiosity's mission. The crater rim towers above the floor, rising about 4.5 kilometers at its highest points. From inside the crater, looking up at those ancient walls, you'd see the scars of impact, the jumbled rocky terrain that marks the boundary between the crater and the surrounding plains. The rim protects the interior from the worst of Mars's dust storms, creating a relatively sheltered environment. The crater floor stretches out in all directions from Mount Sharp, a vast plain covered with wind-blown dunes, scattered rocks, and the subtle traces of ancient water flow. From orbit, scientists had identified what looked like alluvial fans, areas where water had once poured into the crater, spreading sediments in distinctive fan-shaped patterns. They'd seen channels that might have been carved by flowing water. They detected minerals that only form in the presence of water. But orbital observations can only tell you so much. To really understand Gale Crater, to read the detailed history written in its rocks, you need to be there, on the ground, with instruments that can touch and analyze and drill into the stone itself. That's where Curiosity comes in. From its landing site, Curiosity's cameras could see Mount Sharp rising on the horizon, its layered flanks a promise of discoveries to come. But the mission plan didn't call for driving straight to the mountain. First, there was work to do on the crater floor, including investigating an area that orbital observations had identified as particularly interesting, a region called Yellowknife Bay. Mount Sharp dominates Gale Crater in a way that's hard to convey without standing there yourself, which of course, none of us can do. The mountain rises 5.5 kilometers above the crater floor, higher than any mountain in the contiguous United States, higher than Mont Blanc in the Alps. If you stood at Curiosity's landing site and looked toward the mountain, its peak would be lost in the dusty Martian haze long before it reached its summit. But it's not the height that makes Mount Sharp extraordinary. It's what the mountain is made of and how it got there. Every meter of elevation represents millions of years of history. Every layer is a page in the story of how Mars changed from a potentially habitable world to the frozen desert we see today. The mountain's official name is Aeolus Mons, named after the floating island home of the wind gods in Greek mythology. But most people call it Mount Sharp, after the geologist Robert Sharp, who helped train Apollo astronauts and pioneered the study of Martian geology. The name is fitting. Sharp was fascinated by how landscapes evolve over time, how erosion and deposition constantly reshape the surface of a planet. He would have loved to see what Curiosity has discovered on the mountain that bears his name. From orbit, Mount Sharp reveals its sedimentary nature clearly. The layers aren't uniform. Some are thick, light-colored bands that stretch horizontally across the mountain's flanks. Others are thin, darker layers that suggest different materials or different depositional environments. The layers tilt and fold in places, evidence of the forces that have shaped them over billions of years. Near the base of the mountain, the layers appear more regular, more horizontal. These are the oldest deposits, laid down when the crater floor was relatively flat. As you mentally climb higher up the mountain, the layers become more complex. Some show what geologists call cross-bedding, angled layers within larger layers that indicate the sediments were deposited by moving fluids, either water or wind. The upper reaches of Mount Sharp show even more dramatic features. There are cliffs and steep slopes, evidence of harder rock layers that resist erosion. There are valleys and channels carved into the mountainside. And at the very top, the layers seem to drape over the peak, suggesting that the mountain was once entirely buried and has since been exhumed by erosion. Scientists debate exactly how Mount Sharp formed. The sediments clearly accumulated in the crater, but was the crater always open to the outside, allowing rivers to flow in? Or was it at some point a closed basin, a lake that gradually filled with sediment? Did the mountain form entirely from deposition in the crater, or did some of the sediment come from erosion of the crater rim itself, slumping inward over time? These questions might seem academic, but they're crucial to understanding Mars's history. If the crater was a closed lake basin, it would have required a very different climate than Mars has today, with sustained rainfall or snowmelt to fill and maintain the lake. If the sediments came from rivers flowing into the crater, it would tell us about the broader hydrological system that existed on ancient Mars. Curiosity can't answer these questions definitively just by looking at Mount Sharp from a distance. But by climbing the lower slopes, by examining the rocks up close, by analyzing their composition and structure, the rover can piece together the story layer by layer. The mountain isn't the only feature of interest in Gale Crater. The crater floor itself is geologically complex, shaped by billions of years of deposition, erosion, and possibly volcanic activity. There are regions covered by dark volcanic sand, areas where bedrock is exposed, and places where the ancient rocks have been broken and scattered by more recent impacts. One of the most intriguing features on the crater floor is the network of valleys and channels that seem to radiate from the rim down toward the lower elevations near Mount Sharp. These channels, visible from orbit, look exactly like what you'd expect from flowing water. They branch and merge the way rivers do. They have the right proportions, the right patterns. And they connect to deposits that look like they could be ancient deltas or alluvial fans, places where sediment-laden water slowed down and dropped its load. But proving that these features were carved by water requires more than just looking at their shape. Mars is a world where things aren't always what they seem. Features that look like water-carved valleys can sometimes be formed by other processes, like lava flows or catastrophic landslides or even the collapse of underground ice. To know for sure, you need to examine the rocks, to look for the minerals and structures that only form in water. This is why Curiosity's mission focuses so heavily on geology. Every rock tells a story, if you know how to read it. The minerals it contains reveal the conditions under which it formed. The textures and structures show how it was deposited or altered. The chemical composition gives clues about the environment that existed when the rock was created. Gale Crater, with Mount Sharp at its center, is essentially a time machine. The deeper you dig, the older the rocks become. The higher you climb on Mount Sharp, the younger the layers get. By systematically exploring this landscape, by drilling into rocks at different elevations, Curiosity can reconstruct the environmental history of this part of Mars over billions of years. And that's what makes the crater such a perfect laboratory for studying habitability. Life as we know it requires liquid water, a source of energy, and the right chemical ingredients. By reading the rocks of Gale Crater, Curiosity can determine if and when these conditions existed. It can tell us if there was a time when Mars had environments capable of supporting microbial life, even if life never actually arose. From its landing site on the northwestern side of the crater, Curiosity had a long journey ahead of it. The mission plan called for the rover to spend some time investigating the immediate area, then drive to several scientifically interesting locations on the crater floor, and eventually make its way to Mount Sharp. The whole journey would cover many kilometers, through terrain that had never been examined up close. But before undertaking that journey, before driving off toward the mountain on the horizon, Curiosity had work to do close to home. And that work would lead to one of the mission's most important early discoveries, in a place that would become famous in the annals of Mars exploration, Yellowknife Bay. The name Yellowknife Bay comes from Yellowknife, a town in Canada's Northwest Territories. It's a tradition in planetary exploration to name features after places on Earth, particularly places with geological similarities to the Martian location. Yellowknife sits on ancient bedrock, some of the oldest rock exposed anywhere on Earth, and the Canadian Northwest is a place where geologists go to study how our planet looked billions of years ago. The parallel to Mars was clear enough that the name stuck. Curiosity arrived at Yellowknife Bay in December 2012, just a few months after landing. The rover had driven only about half a kilometer from Bradbury Landing, but already the landscape had changed. The landing site had been chosen for its safety, a smooth, boring plain where Curiosity was unlikely to encounter any dangerous obstacles. But boring isn't scientifically interesting, and the mission team was eager to get to more promising terrain. Yellowknife Bay delivered on that promise. From orbit, this area had shown intriguing signs of layered bedrock, material that might hold clues about ancient water. As Curiosity approached, its cameras revealed a landscape unlike anything the mission had seen so far. The ground here was carved into shallow depressions and small ridges, a subtle topography that suggested erosion of underlying bedrock. Dark sand had accumulated in low spots, but in other areas, smooth, light-colored rock was exposed at the surface. The rock wasn't scattered boulders or rubble, but coherent outcrops, actual bedrock that extended beneath the surface. This was exactly the kind of material scientists wanted to investigate. But what really made Yellowknife Bay special wasn't immediately obvious from the surface. It was what the rocks contained, their composition and the story they told about ancient Mars. To understand that story, Curiosity would need to do more than just photograph the rocks. It would need to drill into them, to analyze the powder from deep inside, where the material had been protected from Mars's harsh surface environment for billions of years. On February 8, 2013, Curiosity drilled its first hole on Mars. The location was a flat slab of bedrock nicknamed John Klein, named after a Mars Science Laboratory deputy project manager who had passed away in 2011. The drill bit, about 1.6 centimeters in diameter, bored 64 millimeters into the rock, pulverizing it and bringing the resulting powder up to the surface. This might not sound dramatic, but it was a historic moment. No machine had ever drilled into Martian bedrock and collected a sample before. The Soviet Mars 3 lander had a soil scoop in 1971. The Viking landers had soil scoops in 1976. The Phoenix lander had a scoop in 2008. But none of them could drill into solid rock. None of them could access material that had been sealed away from the surface environment for eons. The powder from that first drill hole was divided among several of Curiosity's instruments. Some went to Shaman, the chemistry and mineralogy instrument, which uses X-ray diffraction to identify the minerals present. Some went to SAM, the sample analysis at Mars instrument, which can detect organic compounds and analyze gases released when the sample is heated. The results were extraordinary. The rock contained clay minerals, specifically a type called smectite. Clays are incredibly significant because they only form in the presence of water, and specifically in water that's relatively neutral in pH. Too acidic or too alkaline, and you get different minerals. The presence of smectite meant that liquid water had interacted with this rock, altering its chemistry and creating these distinctive minerals. But there was more. The rock also contained minerals like magnetite, which suggested that the water had been relatively reducing, meaning it had the right chemistry to support life. In highly oxidizing conditions, like those on Mars's surface today, organic molecules get destroyed quickly. But in a reducing environment, with water present, organic chemistry can flourish. The rock also contained sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon. These are the 6 elements that make up the bulk of life as we know it. Finding all of them together, in an environment that clearly had liquid water, was profound. Within months of landing, barely half a kilometer from where it touched down, Curiosity had accomplished one of its primary objectives. It had found evidence that Mars once had environments capable of supporting microbial life. Not evidence of life itself, but evidence that the conditions were right. Habitability confirmed. The team was thrilled but also cautious. One drill site, one set of measurements, wasn't enough to draw broad conclusions. They needed to confirm the findings with additional samples. So Curiosity drilled again, this time into a target called Cumberland, only about 2.5 meters from the John Klein site. The Cumberland drill hole went even deeper, 70 millimeters, and retrieved similar material. The results confirmed what John Klein had shown. These rocks at Yellowknife Bay had formed in an ancient freshwater lake. The water chemistry had been neutral, perhaps even slightly alkaline. The environment had lasted long enough for sediments to accumulate and for water to permeate the rocks, altering their chemistry. Based on the geological setting, this lake environment had existed for thousands to millions of years, plenty of time for microbial life to have emerged if the right precursor chemistry was present. The rocks themselves told additional details. They were mudstones, fine-grained sedimentary rocks that form when clay and silt settle out of calm water. The fine-grained size meant the water hadn't been flowing rapidly. This wasn't a rushing river but a quiet lake or pond, a place where sediments could gently drift down and accumulate layer by layer. The mudstones contained structures that geologists call concretions, small round nodules where minerals had concentrated. These form when dissolved minerals in water precipitate out, concentrating around some nucleus and growing over time. Their presence was yet another indicator of water permeating through the rock long after it was deposited. There were also small fractures in the rock filled with light-colored minerals, likely calcium sulfate. These mineral veins showed that water had circulated through the rock even after it had lithified, carrying dissolved minerals that precipitated in the cracks. The presence of calcium sulfate specifically is interesting because it forms when sulfate-rich water evaporates, suggesting that the lake environment might have gone through wet and dry cycles. All of these details painted a picture of an ancient Mars very different from the planet we see today. Yellowknife Bay had once been at the edge of a lake, receiving sediments carried by water flowing off the crater rim. The lake was probably fairly shallow enough that its bottom was in what scientists call the photic zone, where sunlight can penetrate. On Earth, that's important because photosynthetic life needs light, and photosynthesis produces oxygen that other organisms can use. The discovery at Yellowknife Bay fundamentally changed how scientists think about early Mars. Before Curiosity, there was debate about whether Mars had ever had stable bodies of liquid water on its surface. Some orbital observations suggested lakes or seas, but the evidence was ambiguous. The chemistry of Martian meteorites hinted at water alteration, but couldn't pin down the details. Yellowknife Bay provided unambiguous evidence. Mars had lakes. The water was fresh and potentially drinkable, not the acidic or briny solutions that some models had predicted. The environment was stable, lasting long enough for thick sequences of mudstone to accumulate. And all the chemical ingredients for life were present. This wasn't just an academic finding. It meant that Mars, at least for some period of its early history, had been a much more welcoming place than previously thought. If life had emerged on Mars, Yellowknife Bay would have been exactly the kind of place where it could have thrived. Of course, finding an environment capable of supporting life isn't the same as finding life itself. Curiosity wasn't designed to detect living organisms or even fossils. Its mission was to assess habitability, to determine if the right conditions existed. And at Yellowknife Bay, it definitively showed that they did. The mission could have ended there, its primary objectives accomplished. But this was just the beginning. Yellowknife Bay represented one moment in Martian history, one environment in one location. To understand how Mars changed over time, to trace the transition from a wet, potentially habitable world to the frozen desert it is today, Curiosity would need to climb Mount Sharp, ascending through layer after layer of sediment, each one representing a different chapter in the planet's story. In July 2013, Curiosity departed Yellowknife Bay and began the long journey toward Mount Sharp. The drive would take over a year and cover almost 7 kilometers, threading through terrain chosen both for its scientific interest and its relative safety. This wasn't just a road trip. Every kilometer was an opportunity to observe the crater floor, to understand the geological context, to see how different regions varied in their composition and structure. The route took Curiosity through areas with exposed bedrock and regions covered by sand dunes. It passed the wreckage of its own landing hardware, bits and pieces of the sky crane and heat shield scattered across the landscape. It drove through what mission scientists called the Kimberley Formation, an area with distinctive layered rocks that showed complex patterns of deposition and erosion. At each stop, Curiosity would deploy its instruments. The Chemistricam laser would zap rocks from a distance, vaporizing tiny spots and analyzing the light emitted to determine composition. The APXS, the alpha particle X-ray spectrometer mounted on the rover's arm, would be pressed against interesting rocks to measure their elemental composition. The MARLI, the Mars Hand Lens Imager, would take extreme close-up photos showing textures and structures invisible to the naked eye. Slowly, kilometer by kilometer, the mountain grew closer. What had been a distant peak on the horizon became a looming wall of layered rock. By September 2014, Curiosity reached the base of Mount Sharp, ready to begin the climb that would take it through billions of years of Martian history. But the journey to this point had already been scientifically rich. The rover had found more evidence of water throughout its traverse. It had seen patterns in the rocks that suggested varying conditions over time, from the lake environment of Yellowknife Bay to drier, perhaps more wind-dominated settings in other areas. The mission was about to enter a new phase, one where every meter of elevation gain would represent ascending through time, moving from the older rocks at the mountain's base to younger deposits higher up. The story was about to get even more interesting. The transition from Yellowknife Bay to Mount Sharp wasn't just a change in location. It was a journey through geological time, and the rocks along the way revealed hints of how Gale Crater had evolved over billions of years. The ancient lake that had deposited the mudstones at Yellowknife Bay hadn't been a permanent feature. Mars's climate had always been variable, and the evidence showed cycles of wet and dry conditions playing out over enormous time scales. During the traverse, Curiosity encountered different types of bedrock that told different stories. Some areas showed conglomerate rocks, sedimentary formations made of rounded pebbles cemented together. These are diagnostic of flowing water, and not just any water but streams or rivers moving fast enough to transport stones the size of your fingernail. The presence of conglomerates meant that water hadn't just pooled in quiet lakes at Yellowknife Bay. It had flowed vigorously across the crater floor, carrying debris from the highlands. The rounded nature of the pebbles was particularly telling. On Earth, river rocks become rounded because they're tumbled against each other as the current carries them downstream. Sharp edges get knocked off. Over distance and time, angular fragments become smooth, round pebbles. The same process had clearly operated on Mars. These rocks had been transported, likely for kilometers, before being deposited and eventually cemented into conglomerate. Curiosity also observed what geologists call cross-bedding in some outcrops, layers of sediment tilted at angles to the main bedding plane. Cross-bedding forms when sand or silt is deposited on the downstream face of a dune or ripple in moving water or wind. As the dune migrates, it leaves behind these angled layers. By looking at the angle and direction of cross-bedding, geologists can figure out which way the water or wind was flowing when the sediment was deposited. The patterns Curiosity observed suggested water flowing generally from south to north, from the crater rim toward the crater's interior where Mount Sharp stands. This made sense. Water flows downhill, and the crater rim is elevated relative to the crater floor. Rain or snowmelt on the rim would have flowed down into the crater, potentially filling it with water or at least creating stream systems that carried sediment inward. But not all the rocks showed evidence of water transport. Some areas were covered by aeolian deposits, sediments laid down by wind. Mars today is a windy place, and it has been for billions of years. Even when Mars had a thicker atmosphere and surface water, wind would have been a major force shaping the landscape. The aeolian deposits were typically finer grained than the water-transported sediments, and they often showed different structures. Wind-deposited layers tend to be more uniform, lacking the rounded pebbles and sharp grain size changes that characterize water deposits. They can also show their own type of cross-bedding, but with different characteristics that trained geologists can distinguish from water-formed cross-beds. The mix of water-deposited and wind-deposited rocks told a story of environmental change. Mars hadn't simply transitioned from wet to dry in a single event. Instead, the planet had likely experienced many cycles, periods when water flowed followed by drier times when wind dominated. The overall trend was toward increasing dryness as Mars lost its atmosphere and its ability to sustain liquid water, but the transition was complex and gradual. One of the most intriguing observations during the traverse was the identification of hematite, an iron oxide mineral. Hematite is interesting because it can form in different ways, and some formation pathways require liquid water while others don't. On Earth, some of the most spectacular hematite deposits form in water-rich environments, precipitating out of iron-rich waters or forming when groundwater alters iron-bearing minerals in rock. Orbital observations had detected hematite in certain regions of Mars years before Curiosity landed, and these detections had been major factors in choosing landing sites for Mars missions. The Mars Exploration Rover Opportunity had explored hematite-rich deposits at Meridiani Planum and found strong evidence that they formed in water. Now Curiosity was seeing hematite too, adding to the evidence that water had been widespread on ancient Mars. The presence of various minerals across Gale Crater created a chemical map of ancient environmental conditions. Clay minerals like those found at Yellowknife Bay indicated neutral pH water. Sulfites suggested more acidic conditions or evaporation of water. Hematite indicated oxidizing conditions. By mapping where different minerals were found, scientists could reconstruct how conditions varied across the crater floor and how they changed over time. As Curiosity approached Mount Sharp, the landscape became more dramatic. The smooth plains gave way to rougher terrain with more exposed bedrock and steeper slopes. The layering in Mount Sharp's flanks became more obvious, great bands of light and dark rock stretching horizontally across the mountain's face. Each layer represented a distinct episode of deposition, a slice of time when sediments accumulated under particular environmental conditions. The mission team had identified a specific entry point to begin climbing the mountain, a region where the slope was gentle enough for Curiosity to safely ascend. This area, called the Murray Formation, was named after Bruce Murray, a planetary scientist who had been a key figure in the early development of Mars exploration. The Murray Formation would prove to be one of the most scientifically valuable targets of the entire mission. Before beginning the climb, Curiosity spent time investigating an area called Pahrump Hills, part of the Murray Formation at the very base of Mount Sharp. The rocks here were finely layered mudstones, similar in many ways to what had been found at Yellowknife Bay. This suggested that the lake environment that had existed at Yellowknife Bay had been more extensive than just that one location. The lake had covered a large portion of the crater floor, with mudstones accumulating across a wide area. The layering in these mudstones was remarkably regular in places, with individual layers just millimeters thick. This kind of fine-scale layering suggested seasonal or cyclical changes in the depositional environment. Perhaps the lake level rose and fell with seasonal changes, or maybe different types of sediment were delivered to the lake at different times of the year. Each thin layer might represent a year or a season, making the rock sequence a kind of calendar recording Martian climate cycles from billions of years ago. Curiosity drilled into the Murray Formation and found similar chemistry to Yellowknife Bay, clay minerals, evidence of neutral pH water, and all the chemical ingredients needed for life. This confirmed that habitable conditions hadn't been limited to a single small area. Gale Crater had hosted a large lake system, perhaps covering hundreds of square kilometers, that persisted for a geologically significant amount of time. The mission team also noticed that the mudstones contained small, light-colored features that looked like crystals. Chemical analysis revealed these were calcium sulfate, likely gypsum. Gypsum forms when sulfate-rich water evaporates, and its presence suggested that the lake had at times partially dried out or that groundwater circulating through the rocks after deposition had carried dissolved sulfates. The interplay between lake deposits, evidence of evaporation, and groundwater alteration painted a picture of a dynamic, changing environment. The lake had likely expanded and contracted over time, perhaps filling during wetter periods and shrinking during drier ones. When the lake shrank, dissolved minerals in the water would have become more concentrated, eventually precipitating out as the water evaporated. These evaporite minerals would then be preserved in the mudstone, creating a chemical record of the lake's history. This kind of environmental dynamism is actually promising from a habitability perspective. On Earth, environments that cycle between wet and dry conditions can concentrate organic molecules and create chemical gradients that life can exploit. The edges of lakes, where water level fluctuates, are often hotspots of biological activity because they offer diverse microhabitats in close proximity. As Curiosity began climbing into the Murray Formation, every meter of elevation gain took it higher into the stratigraphic sequence, into younger rocks that had been deposited later in Martian history. The rover was literally climbing through time, moving from the bottom of the geological record toward the top. The climb was slow and methodical. Curiosity isn't designed for speed. Its top speed is about 150 meters per hour, slower than most people walk, and it typically moves much more cautiously than that, especially when navigating steep or rocky terrain. The mission team back on Earth would examine images of the terrain ahead, plot a safe route, and then upload commands to the rover telling it where to drive. The rover would execute those commands autonomously, using its hazard avoidance systems to stop if it encountered unexpected obstacles. This process of planning, executing, and verifying each drive meant that progress was measured in dozens of meters per day, not kilometers. But slow is safe, and safe is essential when your robot is on another planet with no hope of repair if something goes wrong. Curiosity needed to last years, even decades if possible, and that meant being careful. As the rover climbed, the science team noticed changes in the rocks. Higher up in the Murray Formation, there were layers that showed different characteristics from the mudstones at the base. Some layers contained more sand-sized particles, suggesting higher energy depositional conditions, perhaps areas closer to where streams entered the lake. Other layers showed different mineralogy, indicating changes in water chemistry or source materials over time. One particularly intriguing discovery was the presence of manganese oxides in some rocks. On Earth, manganese oxides typically form in oxidizing conditions, often with the help of microorganisms. While their presence on Mars doesn't prove biology was involved, it does indicate that the oxidizing conditions necessary for their formation existed. This was another piece of evidence about the chemistry of ancient Martian environments, showing that conditions varied from the reducing environment seen in some rocks to more oxidizing conditions in others. The rover also found more organic molecules in the Murray Formation rocks. Organic molecules are molecules containing carbon bonded to hydrogen, and they're the building blocks of life as we know it. But organic molecules can also form through non-biological processes, so their presence alone doesn't indicate life. What their presence does show is that carbon-based chemistry was occurring on ancient Mars, and that organic compounds could be preserved in Martian rocks for billions of years. This last point is crucial. For decades, scientists had debated whether organic molecules could survive on Mars. The planet's surface is bathed in harsh ultraviolet radiation from the sun, and the soil contains strong oxidants like perchlorates that can destroy organic compounds. The general assumption had been that any organic molecules on the surface would be broken down quickly. But Curiosity's find showed that organic molecules could survive if they were protected inside rocks, shielded from radiation and oxidation. The molecules the rover detected were locked in mudstones billions of years old, preserved like fossils. This meant that if life had ever existed on Mars, chemical traces of that life might still be detectable in the right rocks, despite billions of years of exposure to Mars's harsh environment. The types of organic molecules Curiosity detected were relatively simple: chlorobenzene, dichloroalkanes, and other compounds that could form through various processes. The molecules were detected by heating rock samples in the SAM instrument's oven and analyzing the gases released. It's possible that the detected compounds weren't even the original molecules present in the rock but instead were fragments or alteration products created by the heating process or by reactions with perchlorates in the sample. Still, the detection was significant because it showed that carbon-based molecules existed in these ancient rocks. Whether they formed biologically or through purely chemical processes like reactions in hydrothermal systems or delivery by meteorites remained an open question. But at minimum, the findings showed that organic chemistry had been part of Mars's story, and that opens the door to the possibility of past life. As Curiosity continued climbing through the Murray Formation, it covered an elevation gain of tens of meters, ascending through layers that represented millions of years of deposition. Each drilling campaign, each suite of measurements, added detail to the picture of ancient Gale Crater. The lake environment had persisted, but it had changed over time. Water chemistry evolved. Sediment sources shifted. The climate varied, causing the lake to expand and contract. One of the remarkable things about the Murray Formation was its thickness. The formation extends for hundreds of meters in elevation, representing an enormous volume of sediment. On Earth, accumulating that much sediment takes a long time, typically millions of years. If similar rates applied on Mars, then the Murray Formation represented an extended period when conditions were stable enough for continuous deposition. This temporal scale is important for habitability. Life might be able to emerge quickly under the right conditions, but it also might require extended periods of stability to get started. The longer habitable conditions persist, the more opportunity there is for life to arise. The Murray Formation, with its evidence of a long-lived lake system, showed that Mars had provided that opportunity. The lake interpretation for the Murray Formation was supported by multiple lines of evidence. The fine-grained size of the mudstones indicated low-energy deposition, consistent with settling out of quiet water. The presence of clay minerals showed water-rock interaction. The regular layering suggested cycles that might reflect seasonal changes in a lake. The lateral extent of similar rocks across a wide area indicated a large body of water, not just localized puddles or groundwater. But lakes need water sources to persist. Where was the water coming from? Mars's thin atmosphere today can't support much precipitation, and the sun's heat would quickly evaporate any standing water. For a lake to exist, there needs to be a hydrological cycle, evaporation, atmospheric transport, precipitation, and runoff feeding back into the lake. The evidence from Gale Crater suggests that ancient Mars had exactly such a cycle. The crater's rim, rising more than 4 kilometers above the floor, would have been high enough to intercept moisture from the atmosphere. Snow or rain falling on the rim would have run downhill into the crater, feeding streams that carved the channels visible from orbit. Those streams would have carried water and sediment into the crater, maintaining the lake. The lake itself would have been deep enough in places to avoid freezing completely, even if Mars's climate was cold. Liquid water can exist under ice, and many of Earth's coldest environments have ice-covered lakes with liquid water beneath. The mudstones at Yellowknife Bay and in the Murray Formation don't show evidence of glacial influence, suggesting that at least during their deposition, the lake was mostly ice-free, indicating relatively mild conditions. As the mission progressed and Curiosity climbed higher, the rover encountered a geological unit called the Vera Rubin Ridge, a prominent feature on Mount Sharp's lower slopes that had been visible from orbit. The ridge is named after Vera Rubin, an astronomer who provided crucial evidence for the existence of dark matter. Like its namesake, the Vera Rubin Ridge revealed something hidden, a concentration of hematite that gave clues about another chapter in Mars's environmental history. The ridge stands out visually, a resistant layer of rock that forms a distinct topographic high on the mountain's flank. Erosion has carved away softer rocks above and below, leaving the harder rocks of the ridge standing proud. This erosion resistance suggested that the rocks were more strongly cemented or composed of harder minerals, and the hematite concentration likely played a role in that. Curiosity spent many months investigating the Vera Rubin Ridge, drilling multiple samples and conducting extensive surveys with its remote sensing instruments. The rocks here were different from the Murray Formation mudstones. They were more reddish, a color imparted by the hematite. They also contained more evidence of alteration by groundwater after deposition. The hematite itself was a puzzle. There were several ways it could have formed. It might have precipitated directly from iron-rich lake waters. It might have formed when groundwater circulated through the rocks after they were deposited, altering iron-bearing minerals into hematite. Or it might have formed from iron-rich dust or ash that accumulated in the lake and was later altered by groundwater. Analysis of the ridge rocks showed that they contained more silica and less clay compared to the rocks below. This suggested different source materials or different weathering conditions when these sediments were formed. The change in mineralogy might reflect a change in the crater's hydrology or a shift in what areas were eroding and providing sediment to the lake. The ridge also showed evidence of fractures filled with mineral cements, another sign of groundwater flow after the rocks were lithified. Liquid water had percolated through the rocks long after they were initially deposited, carrying dissolved minerals that precipitated in cracks and pore spaces. This groundwater alteration might have occurred thousands or millions of years after the lake dried up, indicating that liquid water in some form persisted in the subsurface even as surface conditions became hostile. These discoveries reinforced a key theme of Curiosity's mission: Mars's watery past was complex and multifaceted. Water wasn't just present in one form at one time. There were surface lakes, flowing streams, groundwater systems, and possibly even snow and ice. These different water reservoirs interacted with rocks in different ways, creating the diverse mineralogy that Curiosity was documenting. The mission's findings were also revealing how Mars's climate changed over time. The lowest rocks, the oldest ones, showed evidence of neutral pH water and reducing conditions, ideal for habitability. Higher up, the rocks showed evidence of more oxidizing conditions and more acidic waters, less favorable for life. The progression suggested that Mars was becoming less habitable over time, even before it lost its surface water entirely. This transition makes sense in the context of Mars's overall evolution. Early Mars had a thicker atmosphere, warmer temperatures, and active volcanism that released gases to help maintain the atmosphere. But Mars is smaller than Earth and cooled faster. Its magnetic field shut down, removing the shield that protected the atmosphere from solar wind erosion. Atmospheric pressure dropped, making liquid water unstable. The climate transitioned from warm and wet to cold and dry. The rocks of Mount Sharp record that transition. The lowest layers were deposited when Mars was most Earth-like. The higher layers show a world in decline, where water was less abundant and conditions were becoming harsher. Climbing Mount Sharp, Curiosity was witnessing the death of a habitable world, reading the autopsy report written in stone. Yet even in the upper rocks that Curiosity explored, there was evidence of water. The planet might have been colder and drier, but it wasn't completely lifeless in the sense of being devoid of water. Liquid water still flowed at times, at least in the subsurface. The possibility of niches where life might have persisted, even as the surface became increasingly hostile, remained. Beyond the Vera Rubin Ridge, Curiosity continued its ascent into what mission scientists called the clay-bearing unit, another distinct geological formation that had been identified from orbit. Orbital spectrometers had detected strong signatures of clay minerals in this region, suggesting another chapter in Gale Crater's water story. Clays, as we've learned, form when water alters volcanic rocks or other minerals over long periods, and different types of clays form under different conditions. The clay-bearing unit represented yet another environment, another set of conditions that existed at some point during the billions of years of sediment accumulation in Gale Crater. Reaching this unit was a major milestone for the mission, years in the planning and execution. When Curiosity finally drilled into clay-rich rocks in April 2019, it was accessing material that might tell a different story from the mudstones of the Murray Formation or the hematite-rich rocks of Vera Rubin Ridge. The chemistry of clay minerals provides windows into past environmental conditions. Some clays form in warm, wet environments with lots of water. Others form in cooler conditions or with less water. The exact species of clay mineral, the elements it contains, and the crystal structure it has are all clues to the temperature, pH, and duration of water exposure when it formed. Curiosity's instruments revealed multiple types of clay minerals in these rocks, suggesting complex alteration histories. Some clays might have formed when the sediments were first deposited in water. Others might have formed later when groundwater circulated through the rock. Distinguishing between these different formation pathways is challenging but important because they tell different stories about Mars's habitability. If the clays formed in surface water environments, it suggests Mars had abundant surface water at the time these sediments were deposited. If they formed from groundwater alteration, it shows that liquid water persisted underground even when the surface was dry. Both scenarios are relevant to habitability, but in different ways. Surface water environments are more accessible to potential life and offer more diverse habitats. Subsurface environments might be more stable over long time periods, protected from the harsh radiation and temperature extremes of the surface. As Curiosity explored the clay-bearing unit, it also observed changes in the physical characteristics of the rocks. Some showed extensive nodules and concretions, similar to what had been seen lower in the section but often larger and more abundant. These features form when dissolved minerals precipitate around nucleation points in the rock, growing over time as mineral-rich groundwater flows through pore spaces. Their abundance suggested significant groundwater activity after the sediments were deposited. The rover also encountered rocks with unusual textures, including some that appeared to have been partially dissolved or altered. On Earth, such features can form when slightly acidic water flows through limestone or other soluble rocks, creating cavities and pits. The features on Mars might have formed similarly, providing evidence of the chemical composition of the water that altered them. One of the ongoing challenges in interpreting Curiosity's data is distinguishing between primary features that formed when the sediment was first deposited and secondary features that formed later through alteration. A rock might be initially deposited as a layer of volcanic ash in a lake. Over time, water circulating through that ash layer alters it, creating clay minerals. Later, when the lake dries up and the rock is exposed at the surface, acidic groundwater might flow through it, dissolving some minerals and precipitating others. Each of these episodes leaves its mark, and teasing apart the sequence of events requires careful analysis. Curiosity's traverse from Yellowknife Bay up through the Murray Formation, over Vera Rubin Ridge, and into the clay-bearing unit covered an elevation gain of more than 300 meters. 300 meters might not sound like much, but in terms of geological time, it represents hundreds of millions to billions of years. The rover ascended through a vertical slice of Mars's history, from the relatively warm and wet early period into the colder, drier transitional period. Each drill sample, each ChemistryCam zap, each Marley close-up image added detail to the evolving picture. Scientists back on Earth would spend years analyzing the data from each location, writing papers, debating interpretations, refining models of how Gale Crater and Mars as a whole evolved. The mission produced more data than could be quickly analyzed, ensuring that discoveries would continue long after Curiosity stopped rolling. The rover itself, despite operating far beyond its original 2-year primary mission, showed remarkable durability. There were wear issues, certainly. The aluminum wheels had holes punched through them by sharp rocks, forcing the mission team to be more careful about the terrain Curiosity traversed. Some instruments showed degradation from years of exposure to radiation and temperature cycles. But overall, the rover remained remarkably capable. Part of this longevity came from careful engineering. Curiosity was built to last, with redundant systems and conservative design margins. Part came from the radioisotope thermoelectric generator that powers the rover. Unlike solar panels, which degrade over time and can be covered by dust, the RTG provides steady power year after year, decade after decade. The plutonium-238 inside the RTG has a half-life of 88 years, meaning Curiosity could theoretically operate for decades if its mechanical and electronic systems hold up. But longevity also came from the skill and dedication of the mission team. When problems arose, the team developed creative solutions. When new science opportunities appeared, they adapted the mission plan to pursue them. The mission wasn't rigidly scripted. It evolved based on what Curiosity found, with the team constantly balancing the desire to explore new areas against the scientific value of detailed investigations at any given location. This adaptability was crucial because Mars kept surprising the mission team. Yellowknife Bay had been more interesting than expected, warranting extended investigation. The Murray Formation turned out to be thicker and more varied than anticipated. Vera Rubin Ridge showed unexpected complexity. Each discovery raised new questions, and answering those questions often meant spending more time at a location than originally planned. The mission also had to adapt to the rover's changing condition. As the wheels wore, the team became more conservative about driving over rocky terrain, taking longer routes when necessary to avoid damage. As power availability changed with the seasons, affecting how much heat the RTG could provide, the team adjusted which instruments were used when. Managing an aging robot on another planet required constant attention and problem-solving. Yet through all these challenges, Curiosity kept producing extraordinary science. The rover had definitively shown that ancient Mars had environments capable of supporting microbial life. It had documented a transition from habitable conditions to harsher environments. It had found organic molecules preserved in ancient rocks. It had traced the history of water in Gale Crater across hundreds of millions of years. These weren't small achievements. These were fundamental contributions to our understanding of Mars and its potential for life. The significance extends beyond Mars itself. Understanding how Mars evolved helps us understand planetary evolution in general. Earth is habitable, Venus is a hellish inferno, and Mars is a frozen desert. Yet all three planets formed at roughly the same time from similar materials. Why did they end up so different? What factors determine whether a planet remains habitable or loses that capability? Mars, being smaller than Earth, provides a case study in what happens when a planet cools too quickly, loses its magnetic field, and can no longer hold onto a thick atmosphere. The transition recorded in Gale Crater's rocks shows that this wasn't an instant catastrophe but a gradual decline that played out over geological time scales. Life, if it ever arose on Mars, would have had time to adapt to slowly changing conditions, potentially finding refuge in subsurface environments even as the surface became uninhabitable. These lessons from Mars inform our search for life elsewhere in the universe. We now know that planets can have habitable periods that end, and that traces of past habitable conditions can be preserved in rocks for billions of years. When we eventually explore other worlds, whether moons in our solar system like Europa or Enceladus, or planets around other stars, we'll be looking for similar evidence: sedimentary rocks, minerals formed in water, organic molecules protected from destruction. Curiosity also demonstrated that we can do sophisticated science robotically on other worlds. The rover carries a rolling laboratory with instruments that can identify minerals by their crystal structure, detect organic molecules at parts per billion concentrations, measure isotopic ratios to understand atmospheric processes, and analyze rocks remotely from meters away using lasers. This technological capability, proven on Mars, paves the way for future missions to even more distant and challenging environments. The mission's success has already inspired follow-on missions. The Perseverance rover, which landed in Gale Crater in February 2021, was built using much of the same technology as Curiosity but with upgraded instruments and a new mission focus, actively searching for signs of ancient microbial life and collecting samples for eventual return to Earth. Perseverance is exploring a different environment from Gale Crater, an ancient river delta, but many of the lessons learned from Curiosity informed the choice of landing site and mission design. Looking at the bigger picture, Curiosity is part of a multi-decade, multi-mission exploration campaign that has transformed our understanding of Mars. The first Mars orbiters in the 1970s showed that Mars had channels that looked like they were carved by water, sparking interest in the planet's hydrological history. The Viking landers in 1976 landed on the surface but found the Martian soil to be hostile to organic molecules, dampening enthusiasm for finding life. The Mars Pathfinder and its Sojourner rover in 1997 demonstrated that mobile exploration was feasible, and the Mars Exploration rover's Spirit and Opportunity, which landed in January 2004, found extensive evidence of past water activity. Curiosity built on these previous missions, bringing more sophisticated instruments and investigating environments that previous missions couldn't reach. And now Perseverance is extending that legacy further, with future missions already in planning stages. Each mission answers some questions but raises new ones, driving the next phase of exploration. That's how scientific exploration works: iterative, incremental, building on what came before. Curiosity's discoveries about habitable environments in Gale Crater have shaped what subsequent missions look for and where they look for it. The organic molecules Curiosity found demonstrated that such molecules can be preserved, encouraging the search for more complex organic compounds that might be biosignatures. The evidence for long-lived lakes has focused attention on ancient lake basins as prime targets for finding evidence of past life. As Curiosity continues climbing Mount Sharp, it's moving into younger geological units, rocks that were deposited later in Martian history when the planet was likely colder and drier. The rover is following the transition from habitable Mars to the Mars we see today, reading the story one layer at a time. Each new drilling campaign, each new analyzed sample, adds another piece to the puzzle of how and why Mars lost its habitability. The work is painstaking. A single drilling campaign can take days of rover operations, and analyzing the samples takes weeks to months as data is downloaded, processed, and scrutinized by scientific teams. The mission doesn't produce instant results. It produces careful, methodical science that builds understanding layer by layer, just like the rocks it studies were built layer by layer billions of years ago. This pace might seem slow in our instant gratification age, but it's the nature of exploring another world. We can't rush to Mars to collect more samples if the first ones are ambiguous. We can't send technicians to repair instruments if they malfunction. Every decision has to be carefully considered because the consequences of mistakes are severe and the opportunities for correction are limited. Yet despite these constraints, or perhaps because of them, the mission has achieved remarkable things. Curiosity has driven more than 35 kilometers across the Martian surface. It has taken hundreds of thousands of images. It has fired its laser more than 900,000 times. It has drilled dozens of holes into Martian rocks and analyzed the powder with sophisticated laboratory instruments. It has measured radiation levels that future human explorers will face. It has characterized the Martian atmosphere and detected mysterious variations in methane concentrations. It has watched dust devils dance across the crater floor and tracked clouds drifting across the butterscotch sky. Most importantly, it has shown us that Mars was once a world where life could have emerged and thrived. Whether life actually did emerge remains unknown. Curiosity wasn't designed to detect life itself, only to assess habitability. But by demonstrating that Mars had liquid water, neutral pH, all the necessary chemical ingredients, and stable environments that persisted for geologically significant time periods, Curiosity has shown that Mars gave life a chance. The question now isn't whether Mars could have supported life, but whether life arose to take advantage of the opportunities that ancient Mars provided. That question will drive Mars exploration for decades to come. Future missions will search for more definitive biosignatures, chemical or structural evidence that can only be produced by life. Eventually, samples collected by Perseverance and potentially other rovers will be returned to Earth where they can be analyzed with laboratory instruments far more sophisticated than anything we can send to Mars. And someday, humans will walk on Mars themselves, exploring with a flexibility and intelligence that no robot can match, bringing the quest to understand Mars and its history to a new level. When that happens, when the first human stands on the rim of Gale Crater and looks down at Mount Sharp, they'll be seeing a landscape that Curiosity helped us understand. The knowledge gained from this mission, the maps it created, the analyses it performed, will be part of the foundation that makes human exploration possible. Curiosity is a pioneer, blazing a trail that others will follow. For now, though, the rover continues its solitary work, climbing slowly up Mount Sharp, drilling into rocks, analyzing samples, and sending data back to Earth. Every day is a new opportunity to learn something about Mars. Every image might capture something unexpected. Every measurement might reveal a new piece of the puzzle. Somewhere on Mars, right now, as you're hearing these words, Curiosity sits on a mountainside. The sun is rising or setting over Gale Crater, painting the sky in colors alien to Earth. The thin wind is blowing dust across ancient rocks. And a robot built by humans, powered by plutonium, is reading the history of another world, looking for answers to questions we've asked for generations. Are we alone? Could life exist beyond Earth? What is our place in the universe? The story continues in part 2, where we'll explore more of Curiosity's discoveries, including the mysterious methane detections, the continued climb up Mount Sharp into even younger geological units, and what all these findings tell us about Mars's transformation from a potentially habitable world to the frozen desert we see today. We'll look at how Curiosity's instruments work, diving into the technology that makes these discoveries possible, and we'll examine what the mission means for the future of Mars exploration and humanity's eventual journey to the Red Planet. The evidence for ancient water on Mars isn't a single smoking gun. It's a tapestry woven from dozens of observations, measurements, and analyses, each thread strengthening the overall picture. Every time Curiosity drills into a rock, zaps it with a laser, or photographs it in microscopic detail, it's adding to our understanding of how water shaped Gale Crater and, by extension, how water shaped Mars. Water leaves its mark in many ways. It carves channels and shapes landscapes. It dissolves some minerals and precipitates others. It alters rocks chemically, creating new minerals that wouldn't exist without liquid water. It transports sediments, sorting them by size and depositing them in distinctive patterns. Each of these processes creates evidence that can survive for billions of years, waiting for a rover like Curiosity to come along and read the story. The rounded pebbles in the conglomerate rocks near the landing site were among the first clear pieces of evidence. Rounding happens through abrasion during transport in flowing water. The more distance the pebbles travel, the rounder they become. The size of the pebbles also tells us about the water's velocity. Larger stones require faster moving water to transport them. The conglomerates Curiosity found contain pebbles several millimeters to a centimeter across, indicating streams flowing at least ankle deep and moving fast enough to have a distinct current. The patterns of crossbedding in some rock formations provided additional evidence. Crossbedding forms when sediments are deposited on the sloped face of an underwater dune or ripple. As the dune migrates, it leaves behind angled layers. By examining the angle and direction of these layers, scientists can reconstruct which way the water was flowing, how deep it was, and how fast it moved. The cross-bedded rocks in Gale Crater showed flow patterns consistent with streams entering the crater from the south, flowing down from the crater rim toward the interior. But the most compelling evidence for water came from mineralogy. Clay minerals, especially the smectites found at Yellowknife Bay and elsewhere, only form when water interacts with volcanic rocks over extended periods. The water can't be just any water. It needs to be relatively neutral in pH, not too acidic and not too alkaline. In highly acidic conditions, clays break down and other minerals like sulfates form instead. In highly alkaline conditions, yet other minerals predominate. The presence of abundant clay minerals told Curiosity's science team that liquid water with near-neutral pH had soaked these rocks. The type of clay mineral matters too. Smectites form at moderate temperatures, typically between freezing and about 80 or 90 degrees Celsius. This temperature range is compatible with surface water environments like lakes or groundwater at shallow depths. Other types of clay minerals, like chlorites, form at higher temperatures and usually indicate deeper burial or hydrothermal alteration. By identifying the specific clay minerals present, scientists could constrain the temperature and pressure conditions when the water alteration occurred. Calcium sulfate minerals, like the gypsum veins Curiosity observed throughout the Murray Formation, provided evidence of a different aspect of Mars's water story. Gypsum forms when sulfate-rich water evaporates. When a lake dries up, or when groundwater seeps through rock and then evaporates at the surface, the dissolved minerals it carries become concentrated and eventually crystallize. The presence of gypsum veins cutting through the mudstone showed that the rocks had been exposed to sulfate-rich waters after they were initially deposited. This tells us that Gale Crater's lake probably went through cycles of filling and drying, expanding during wetter periods and contracting during drier ones. As the lake shrank, the water would have become more concentrated in dissolved salts, eventually becoming briny. When it dried completely, minerals like gypsum would precipitate out, coating the former lake bed. Later, when water returned, new sediments would be deposited on top of the evaporite minerals, and the cycle would continue. These wet-dry cycles are actually quite important for the habitability question. On Earth, environments that alternate between wet and dry can concentrate organic molecules and create interesting chemistry that might be relevant for the origin of life. Some researchers think that life might have originated in such fluctuating environments rather than in permanently wet conditions, because the dry phases can drive chemical reactions that assemble more complex molecules from simpler precursors. Curiosity also found evidence for different types of water environments at different times. The mudstones at Yellowknife Bay indicated a calm, deep lake where fine sediments could settle undisturbed. The conglomerates elsewhere showed vigorous stream flow. The evaporite minerals indicated periods when the lake was shrinking and becoming more saline. The groundwater alteration features showed that liquid water circulated through the rocks long after surface water was gone. This diversity of water environments over time painted a picture of a dynamic, changing landscape. Ancient Gale Crater wasn't a static, boring place. It was active. Streams flowed. Lakes rose and fell. Groundwater circulated. Conditions changed with the seasons and over longer climate cycles. This dynamism is encouraging from a habitability standpoint because diverse, changing environments create ecological opportunities that stable, unchanging environments don't provide. One of the more subtle pieces of evidence for water came from the grain size distribution in the mudstones. When sediment settles out of water, the larger, heavier particles settle first, and the finest particles settle last. If you look at a single layer of sediment deposited in a lake, you often see this pattern, coarser material at the bottom grading to finer material at the top. This is called graded bedding, and it's diagnostic of deposition from water, especially water that's slowing down or settling after being stirred up. Curiosity observed graded bedding in some of the Murray Formation mudstones, another confirmation that these rocks were deposited in a lake. The presence of extremely fine-grained layers, where individual particles are only a few micrometers across, indicated that the water had been very calm when those layers formed. Only in still water can such fine particles settle out rather than being kept in suspension by turbulence. The thickness of the mudstone layers also told a story. Some layers were millimeters thick, suggesting they were deposited over short time periods, perhaps a season or a year. Other layers were thicker, indicating longer depositional periods. The pattern of thin and thick layers might reflect climate variations, with thicker layers deposited during wetter periods when more sediment was being washed into the lake, and thinner layers during drier times when less sediment was available. Scientists can even estimate how long the lake existed based on the total thickness of lake sediments and reasonable estimates of deposition rates. On Earth, lakes typically accumulate sediment at rates of millimeters to centimeters per year, depending on how much sediment is being delivered. If similar rates applied on Mars, then the hundreds of meters of mudstone in the Murray Formation could represent millions of years of continuous or intermittent lake conditions. That's a long time, plenty long enough for interesting chemistry to occur and, potentially, for life to get started if the right ingredients came together. The evidence for water wasn't limited to the ancient past. Curiosity also detected signs of more recent water activity, though on a much smaller scale. Some rocks showed what are called dendritic patterns, branching structures that looked like they might be formed by briny water seeping through cracks in the recent past, geologically speaking. Mars today has no liquid water on its surface because the atmospheric pressure is too low, but brines, water with lots of dissolved salts, can remain liquid at lower pressures than pure water. It's possible that brines occasionally form during warmer parts of the day or season, trickle down slopes, and leave mineral deposits before freezing or evaporating. Curiosity also observed what might be ancient shoreline features, subtle changes in rock types and textures at consistent elevations that could mark the edge of the ancient lake. Identifying shorelines on Mars is tricky because billions of years of erosion can obscure them, but if confirmed, such features would provide powerful evidence for standing bodies of water and could even help estimate how deep the lake was. The geochemistry of the rocks provided yet another line of evidence. When water flows over rocks, it preferentially dissolves certain elements and leaves others behind. By measuring the elemental composition of rocks at different locations and at different stratigraphic levels, scientists can look for the signatures of this chemical weathering. Elements like sodium and potassium are more easily dissolved and transported by water, while elements like aluminum and titanium are less mobile and tend to concentrate in the weathered residue. Curiosity's APXS instrument measured these elemental patterns, finding signatures consistent with extensive water alteration. Isotopic ratios provide additional evidence. Water molecules come in different isotopic varieties depending on whether they contain light or heavy isotopes of hydrogen and oxygen. When water evaporates, the lighter isotopes preferentially escape to the atmosphere, enriching the remaining liquid in heavier isotopes. By measuring the isotopic composition of minerals that formed in water, scientists can learn about the evaporation history of that water. Curiosity's SAM instrument made some of these measurements, finding isotopic patterns consistent with evaporation, another piece of evidence for lakes that shrank and dried over time. All these lines of evidence converge on the same conclusion: liquid water was abundant in Gale Crater for extended periods during Mars's early history. The water created habitable environments where all the necessary ingredients for life were present. Whether life actually arose is still unknown, but the opportunity was there, and understanding that opportunity is a major accomplishment of the Curiosity mission. The minerals Curiosity discovered in Gale Crater aren't just evidence of past conditions. They're historical records, chemical fossils that preserve information about the environments where they formed. Each mineral species has a story to tell about temperature, pressure, water chemistry, and available elements. By cataloging the minerals present and understanding their spatial distribution, scientists can reconstruct the environmental history of the crater in remarkable detail. Clay minerals have been a recurring theme in Curiosity's discoveries. These are phyllosilicates, sheet-structured minerals that contain water molecules within their crystal lattice. On Earth, clays form through weathering of volcanic rocks or through direct precipitation from water. The specific type of clay mineral that forms depends on the starting rock composition, the pH and chemistry of the water, the temperature, and how long the reaction proceeds. The smectite clays found at Yellowknife Bay and in the Lower Murray Formation are particularly interesting. Smectites form in neutral to slightly alkaline pH conditions at moderate temperatures. They're stable over geological time and resist further alteration unless conditions change dramatically. Their presence told the Curiosity team that the water in ancient Gale Crater had been benign, not acidic or hypersaline, the kind of water where Earth-like microorganisms could thrive. But Curiosity also found other types of clays, including what might be chlorites or vermiculites in some locations. These clays form under slightly different conditions, suggesting that water chemistry varied across the crater or changed over time. Mapping these mineralogical variations helped scientists understand the full range of environments that existed in ancient Gale Crater. Sulfate minerals, particularly calcium sulfate in the form of gypsum and basanite, were abundant throughout much of the stratigraphic section. Sulfates on Mars have been known since orbital observations in the early 2000s revealed extensive sulfate deposits in various regions of the planet. The Mars Exploration Rover Opportunity spent years exploring sulfate-rich deposits at Meridiani Planum, finding evidence that they formed in acidic, evaporative conditions. The sulfates in Gale Crater tell a similar story of evaporation, but the context is different. At Yellowknife Bay and in the Murray Formation, the sulfates occur as veins and nodules within mudstones that also contain clays. This suggests that the sulfates formed later than the clays, likely when the lake environment was drying out or when groundwater rich in dissolved sulfates circulated through the already deposited sediments. The source of the sulfate is an interesting question. On Earth, sulfates in sedimentary environments often come from the weathering of sulfide minerals or from volcanic gases that dissolve in water and oxidize to form sulfuric acid. Mars has plenty of volcanic history, and volcanic emissions would have been a major source of sulfur to the atmosphere and hydrosphere. When this sulfur dissolved in water and interacted with rocks containing calcium, gypsum would precipitate. Hematite, the iron oxide mineral that gave Vera Rubin Ridge its distinctive reddish color, provided evidence of oxidizing conditions. Iron is one of the most abundant elements on Mars, giving the planet its characteristic red color. But iron can exist in different oxidation states, and the specific iron minerals that form depend on how oxidizing or reducing the environment is. Hematite is a fully oxidized form of iron, requiring oxygen or other oxidants to form. Its concentration in Vera Rubin Ridge suggested that the conditions when these rocks formed or were altered involved oxidizing waters. This could mean that the atmosphere at that time contained more oxygen, or that the water itself carried oxidizing compounds. Either way, it represented a different chemical environment from the more reducing conditions indicated by the minerals at Yellowknife Bay. This difference is significant because it suggests environmental change over time. The older rocks, lower in the stratigraphic sequence, indicated reducing conditions favorable for preserving organic molecules and potentially supporting life. The younger rocks, higher in the sequence, showed more oxidizing conditions that would have been harsher for organic chemistry and life. This progression matches the broader narrative of Mars changing from a more habitable to less habitable world over time. Magnetite, another iron oxide mineral, was found in some rocks. Magnetite forms in less oxidizing conditions than hematite, and its presence alongside other minerals provided clues about the oxygen levels in ancient Gale Crater's water. On Earth, magnetite is sometimes produced by certain types of bacteria that use iron in their metabolism. The magnetite on Mars could have formed biologically or through purely chemical processes, and distinguishing between these possibilities would require more detailed analysis than Curiosity can provide. Silica minerals, including possible opal and tridymite, were detected in some areas. Tridymite is particularly interesting because it's a high-temperature form of silica that's rare on Earth and usually associated with silica-rich volcanic rocks or high-temperature alteration. Its presence on Mars was unexpected and suggested that either the source rocks for the sediments were unusually silica-rich, or that high-temperature processes had been involved at some point in the rock's history. Silica also forms when volcanic rocks weather in water, with silica dissolving and then precipitating out as the water chemistry changes or as it evaporates. Silica-rich deposits on Earth can form in hot springs, where the high temperature increases silica solubility, and then the silica precipitates when the water cools or evaporates. If similar processes occurred on Mars, they might indicate hydrothermal systems where hot water circulated, potentially providing energy and nutrients for hypothetical microbial ecosystems. Curiosity also detected boron in some rocks, a surprising find that made headlines. Boron is a relatively rare element, but it's important for life on Earth because it helps stabilize ribose, a sugar molecule that's a key component of RNA. RNA is thought to have been crucial in the origin of life, preceding DNA in early cellular organisms. The presence of boron in Mars's ancient lake sediment suggests that one more piece of the habitability puzzle was present. It doesn't prove life existed, but it shows that yet another ingredient thought to be important for life was available. The presence of perchlorates, chlorine-oxygen compounds, was another significant discovery. Perchlorates are strong oxidants and are toxic to most Earth life, but they're widespread on Mars. Curiosity detected perchlorates in soil samples and also found chlorinated organic compounds when heating rock samples, likely indicating reactions between organic molecules and perchlorates during the heating process. Perchlorates are a double-edged sword for habitability. On one hand, they're strong oxidants that can destroy organic molecules, making the preservation of biosignatures more difficult. On the other hand, some Earth microorganisms can use perchlorates as an energy source, breathing them the way we breathe oxygen. If life ever existed on Mars, perhaps some organisms adapted to use perchlorates, turning a potential toxin into a metabolic resource. The mineral assemblages Curiosity documented also provided information about post-depositional changes to the rocks. Many of the minerals showed evidence of having been altered after the original sediments were deposited. Groundwater flowing through the rocks dissolved some minerals and precipitated others. Temperature changes as the rocks were buried and then exhumed caused some minerals to transform into different forms. Exposure to the Martian atmosphere over billions of years altered the surface chemistry. Distinguishing these different generations of minerals and understanding the sequence of alterations is challenging but essential for reconstructing the complete history. A single rock might have been deposited as volcanic ash in a lake 3.5 billion years ago, altered to clay minerals by the lake water, buried under subsequent sediments, altered again by groundwater circulating through fractures, partially lithified into solid rock, eroded and exposed at the surface, and then altered yet again by atmospheric weathering. Each of these events would leave its chemical and mineralogical signature, and teasing apart this complex history requires careful integration of multiple lines of evidence. The mineralogical diversity Curiosity found is itself significant. More than a dozen distinct minerals have been identified, and likely more will be found as data analysis continues. This diversity indicates complex geochemistry, multiple episodes of water activity under varying conditions, and a long and eventful geological history. It's exactly the kind of complexity you'd hope to find in an environment that might have supported life. Reconstructing ancient climates on another planet is extraordinarily challenging. On Earth, we have ice cores, tree rings, sediment cores from lake beds and ocean floors, and countless other climate records spanning millions of years. On Mars, we have rocks observed by rovers and orbital imagery. Yet even with limited data, scientists can piece together a surprisingly detailed picture of how Mars's climate evolved. The rocks in Gale Crater indicate that early Mars, at least 3.5 billion years ago, had a climate capable of sustaining liquid water at the surface. This requires temperatures above freezing, at least seasonally, and atmospheric pressure high enough that liquid water doesn't immediately boil away. Today's Mars has surface temperatures that average -63 degrees Celsius and atmospheric pressure less than 1% of Earth's. Liquid water can't exist under these conditions except possibly as brines in specific circumstances. For ancient Mars to have had stable lakes and flowing rivers, the climate must have been fundamentally different. The atmosphere needed to be thicker, providing more pressure and also acting as a greenhouse blanket to trap heat. Mars receives only about half the sunlight per square meter that Earth does because it's farther from the Sun, so without a greenhouse effect, the planet would be even colder than it is today. What could have made early Mars warm enough for liquid water? Several possibilities have been proposed. Early Mars had active volcanism, which would have released greenhouse gases like carbon dioxide and water vapor into the atmosphere. A thicker carbon dioxide atmosphere could have provided some warming, though climate models suggest that carbon dioxide alone might not have been enough to keep Mars warm. Perhaps other gases like methane or hydrogen were also present, enhancing the greenhouse effect. Another possibility is that early Mars was warmer because the Sun was actually a bit different. The faint young Sun paradox notes that the Sun was about 70 to 75% as bright 4 billion years ago as it is today. This would have made Mars even colder, seemingly contradicting the evidence for liquid water. Resolving this paradox requires either a very effective greenhouse atmosphere or alternative warming mechanisms like impact heating or geothermal heat from Mars's interior. The geological evidence in Gale Crater provides constraints on climate models. The presence of clay minerals formed at moderate temperatures limits how hot the climate could have been. The evidence for lakes that filled and dried suggests climate variability, possibly seasonal cycles or longer-term oscillations. The transition from clay-rich rocks at the bottom of the sequence to sulfate-rich rocks higher up suggests increasing aridity over time as the climate dried out. The clay minerals themselves offer clues about temperature and rainfall. On Earth, smectite clays form through chemical weathering of volcanic rocks under conditions with moderate rainfall and temperatures. If the same principles apply on Mars, then the abundance of smectites in Yellowknife Bay and the Lower Murray Formation suggests that these areas experience sustained water exposure, possibly from rainfall or snowmelt percolating through volcanic soils and rocks. The conglomerates with rounded pebbles indicate flowing water with enough energy to transport stones. Estimating the flow rates required to move pebbles of the observed sizes gives hydrologists information about how much water was moving through the system. Combined with estimates of the crater's drainage basin, this allows rough calculations of precipitation rates. The numbers that come out suggest rainfall or snowmelt equivalent to at least tens of centimeters per year, comparable to semi-arid regions on Earth. The presence of lake sediments hundreds of meters thick implies that the lake existed for a long time, likely millions of years at minimum. Lakes need sustained water input to persist, especially in an environment where evaporation is occurring. The persistence of the Gale Crater Lake suggests a climate stable enough to maintain hydrological cycling over geological time scales, not just brief warm periods punctuating an otherwise frozen world. However, the evidence for evaporite minerals and wet-dry cycles indicates that the climate wasn't constantly wet. There were drier periods when the lake shrank or even dried up completely. This variability could have been driven by changes in Mars's orbital parameters. Like Earth, Mars experiences changes in its axial tilt and orbital eccentricity over time, and these changes affect the seasonal and latitudinal distribution of sunlight, driving climate variations. Mars's axial tilt, in particular, varies much more dramatically than Earth's does because Mars lacks a large moon to stabilize its rotation. Over millions of years, Mars's tilt can vary from about 15 degrees to more than 35 degrees. Higher tilt values lead to more extreme seasons and can cause polar ice to sublimate, thickening the atmosphere temporarily. These orbital variations likely drove climate cycles that would have affected lake levels in Gale Crater and elsewhere. The transition from a warm, wet early Mars to the cold, dry planet we see today didn't happen overnight. The stratigraphic sequence in Gale Crater records this transition, with the lower rocks showing more evidence of water and habitable conditions, and the upper rocks showing increasingly arid conditions. This transition likely occurred over hundreds of millions to a billion years, driven by the gradual loss of Mars's atmosphere. Mars lost its atmosphere through multiple processes. The planet's weak magnetic field couldn't protect the atmosphere from solar wind, charged particles from the Sun that strike the upper atmosphere and strip away molecules. Volcanic outgassing, which on Earth continuously replenishes atmospheric gases, slowed and eventually largely ceased on Mars as the planet's interior cooled. Large asteroid impacts in Mars's early history might have blasted portions of the atmosphere into space. Over time, these processes eroded away the thick atmosphere that early Mars had, dropping the pressure and ending the greenhouse warming. The evidence from Curiosity suggests this atmospheric loss wasn't uniform but might have occurred in stages. There may have been periods when the atmosphere temporarily thickened due to increased volcanic activity or orbital variations causing polar ice to sublimate, creating transient warm periods when water flowed again. But the overall trend was toward atmospheric thinning and climate cooling. By analyzing the sequence of rock types and minerals in Gale Crater, scientists can place the major climate transitions in a timeline. The habitable conditions evident at Yellowknife Bay and the Lower Murray Formation existed in the Hesperian period of Martian history, between about 3.7 and 3 billion years ago. The more arid conditions seen in higher stratigraphic levels likely represent the transition into the Amazonian period, which continues to the present day and is characterized by a cold, dry, hyperarid climate. Understanding Mars's climate history isn't just an academic exercise. It informs the search for life by identifying when and where habitable conditions existed. It also provides lessons about planetary habitability in general. Mars shows us that a planet can have habitable surface conditions and then lose them, and that this transition can occur over geological time scales. This is relevant for understanding exoplanets, planets around other stars, where we're trying to determine which ones might support life based on limited observational data. The instruments aboard Curiosity aren't just scientific tools. They're marvels of engineering, each one designed to overcome the challenges of operating on another world. Understanding what these instruments do and how they do it helps appreciate the sophistication of the science Curiosity performs every day. The Chemistry Cam, short for chemistry and camera, is one of the rover's most distinctive instruments. It uses a laser to vaporize tiny spots on rocks from up to 7 meters away, then analyzes the light emitted by the vaporized material to determine its composition. This technique, called laser-induced breakdown spectroscopy, allows Curiosity to analyze rocks without having to drive up to them and place an instrument in contact. The ChemistryCam laser pulses 50 times per second, each pulse delivering about 14 millijoules of energy. That might not sound like much, but focused on a spot less than half a millimeter across, it's enough to heat the rock to plasma temperatures, tens of thousands of degrees. The plasma emits light at specific wavelengths characteristic of the elements present. By analyzing this light with 3 spectrometers covering ultraviolet, violet, and visible to near-infrared wavelengths, ChemistryCam can identify more than 20 elements. ChemistryCam has been extraordinarily productive, having fired its laser more than 900,000 times as of late 2025. It's analyzed thousands of targets, providing compositional data that helps the science team decide which rocks are interesting enough to warrant closer examination with other instruments. ChemistryCam can also remove dust and weathering rinds from rocks by repeatedly zapping the same spot, allowing analysis of fresher rock beneath. The Alpha Particle X-ray Spectrometer, APXS, is mounted on the rover's robotic arm and must be placed directly against or very close to a rock or soil sample. It uses radioactive curium to generate alpha particles and X-rays that interact with the sample, causing it to emit its own X-rays characteristic of its elemental composition. By measuring these emitted X-rays, APXS can determine the abundance of most elements from sodium to heavier elements. APXS measurements take hours because the signals are weak and require long integration times to get good statistics. The rover typically presses the APXS against a rock before nightfall, lets it run all night when there's less daylight available for other activities, and then retrieves the data in the morning. Despite the slow pace, APXS has analyzed hundreds of targets, providing detailed elemental compositions that complement ChemistryCam's remote analyses. The Mars Hand Lens Imager, MARLI, is essentially a high-powered magnifying glass combined with a high-resolution camera. Also mounted on the rover's arm, MARLI can take extreme close-up images with resolution fine enough to see individual sand grains and rock textures invisible to the naked eye. It can focus from about 2 centimeters away up to infinity, allowing it to photograph everything from microscopic details to landscape views. MARLI has been crucial for understanding rock textures and structures. It can reveal whether a rock is made of rounded or angular grains, whether it's been abraded by wind, whether it contains crystals or concretions, and countless other details that help geologists interpret how the rock formed. Some of MAHLI's most striking images show layering on scales of millimeters, preserving details of depositional processes from billions of years ago. The Chemistry and Mineralogy Instrument, SHAMAN, is an X-ray diffraction and X-ray fluorescence instrument housed inside the rover's body. When Curiosity drills a rock or scoops soil, some of the sample can be delivered to SHAMAN for analysis. SHAMAN determines what minerals are present by how they diffract X-rays. Each mineral has a unique diffraction pattern, like a fingerprint, allowing positive identification. SHAMAN's discoveries have been fundamental to understanding Gale Crater's history. It identified the smectite clays at Yellowknife Bay, definitively showing that neutral pH water had altered these rocks. It found the calcium sulfate minerals that indicated evaporation. It detected feldspar, pyroxene, olivine, and other minerals that revealed information about the volcanic rocks that were the source for the sediments. Every mineral identification added detail to the story of ancient Mars. The sample analysis at Mars Instrument, SAM, is the most complex instrument on Curiosity, actually a suite of 3 instruments: a quadrupole mass spectrometer, a gas chromatograph, and a tunable laser spectrometer. SAM analyzes gases in the Martian atmosphere and gases released when rock or soil samples are heated in small ovens. SAM can detect organic molecules at parts per billion concentrations, far more sensitive than any previous in situ instrument on Mars. It can identify specific organic compounds by their mass and by their behavior in the gas chromatograph. It can measure isotopic ratios, determining not just what elements are present but what isotopes of those elements, providing clues about planetary processes and history. SAM's detection of organic molecules in Martian rocks was a landmark discovery. Previous missions had struggled to find organics, leading to questions about whether they existed or were just too difficult to detect. SAM showed that organics were there, preserved in ancient rocks, waiting to be found. The instrument also analyzed atmospheric gases, measuring the seasonal variations in carbon dioxide and detecting trace amounts of methane, a finding that would lead to one of the mission's most intriguing mysteries. The rover also carries environmental monitoring instruments. The Radiation Assessment Detector, RAD, measures the radiation environment on Mars's surface, important data for planning future human missions. Astronauts traveling to Mars and working on the surface will be exposed to radiation from cosmic rays and solar particles, and understanding the exposure levels helps engineers design appropriate shielding. The Rover Environmental Monitoring Station, REMS, measures temperature, pressure, humidity, wind speed and direction, and ultraviolet radiation. These measurements help characterize Mars's weather and climate on a day-to-day basis and provide context for interpreting the geological record. Knowing current conditions helps scientists understand how modern Mars differs from the ancient environments recorded in the rocks. The Dynamic Albedo of Neutrons instrument, DAN, uses a neutron generator to probe for hydrogen in the soil, which indicates the presence of water or hydroxyl-bearing minerals. As Curiosity drives, DAN continuously measures the soil beneath it, creating a map of water abundance. While it hasn't found significant near-surface water ice at Gale Crater, the data it's collected helps understand the distribution of water-bearing minerals. The mast camera, MASTCAM, consists of 2 cameras with different focal lengths mounted on the rover's mast about 2 meters above the ground. MASTCAM provides the dramatic color landscape images that have become iconic representations of Mars exploration. But it's also a scientific instrument, with filters that allow imaging in specific wavelengths to distinguish different minerals and rock types. All these instruments work together, each providing different information that helps build a complete picture. ChemistryCam might identify an interesting rock composition from a distance. Marley would then photograph it up close to see its texture. APXS would provide detailed elemental composition. If the rock seemed particularly interesting, the rover might drill it, delivering samples to Shaman to identify minerals and to SAM to search for organics. Each instrument contributes a piece of the puzzle, and only by combining all the pieces can scientists fully interpret what they're seeing. The data from these instruments doesn't provide instant answers. It requires careful calibration, processing, and interpretation. Scientists back on Earth spend weeks to months analyzing data from a single drilling campaign, comparing it to laboratory experiments, to samples from other locations, to theoretical models. The science is methodical and rigorous, with peer review and debate about interpretations before conclusions are published. This is why missions like Curiosity take years to produce their full scientific return. The rover might operate for a decade, but the data it produces will be analyzed for decades more, with new insights emerging as scientists develop better analysis techniques and as new context becomes available from other missions. The journey up Mount Sharp has been the defining objective of Curiosity's extended mission. After confirming habitable conditions on the crater floor at Yellowknife Bay, the rover's primary goal became ascending through the stratigraphic sequence, climbing through time to understand how Mars's environment evolved. Curiosity reached the base of Mount Sharp in September 2014, about 2 years after landing. The route to the mountain had been carefully planned to balance scientific interest with driving safety. The rover couldn't just drive straight to the mountain because the terrain included sand dunes and rocky obstacles that would have been difficult or dangerous to cross. Instead, the route wound through areas with exposed bedrock and interesting geology, turning the drive into a scientific investigation in its own right. Upon reaching Mount Sharp, Curiosity began systematically ascending through the Murray Formation, the thick sequence of mudstone that formed in the ancient lake. The formation was named after Bruce Murray, a Caltech planetary scientist who had been a champion of Mars exploration and served as director of NASA's Jet Propulsion Laboratory from 1976 to 1982. Murray had been a driving force behind the Viking missions and had advocated for continued Mars exploration throughout his career. Naming this formation after him honored his contributions to the scientific understanding of the Red Planet. The Murray Formation is remarkably thick, extending more than 300 meters in elevation up the side of Mount Sharp. Climbing through it required years of driving, punctuated by stops to analyze particularly interesting outcrops. The formation isn't uniform. It shows variations in grain size, color, layering patterns, and mineralogy that reflect changes in depositional conditions over the millions of years it was accumulating. In some areas, the Murray Formation mudstones were distinctly reddish, colored by iron oxides. In other areas, they were more gray or purple. These color variations reflect different oxidation states of iron, which in turn reflect the chemistry of the water environment when the rocks formed or were later altered. Gray rocks indicated more reducing conditions, while red rocks indicated oxidizing conditions. Mapping these color variations helped scientists understand the spatial and temporal variations in water chemistry. The layers within the Murray Formation told stories about the lake's history. Thin, fine-grained layers suggested quiet water with little sediment input. Thicker, coarser layers suggested periods when more sediment was being delivered, perhaps during seasonal floods when streams flowing into the crater carried higher loads. Some layers showed ripple marks, small-scale wavy patterns formed by water moving over sediment. These ripples, preserved for billions of years, recorded current directions and water depths from the ancient lake. As Curiosity climbed higher, the science team noticed changes that suggested the environment was becoming more arid. The abundance of clay minerals decreased while sulfate minerals became more common. The rock textures changed, with more evidence of evaporation and less evidence of standing water. These changes supported the hypothesis that Mars's climate was drying over time, with the lake in Gale Crater shrinking and eventually disappearing as the planet lost its atmosphere and the climate cooled. One of the major targets on Mount Sharp was the Vera Rubin Ridge, a prominent topographic feature about 250 meters above the base of the mountain. The ridge had been visible from orbit as a darker, more resistant layer standing out from the surrounding terrain. Orbital spectrometers detected hematite in the ridge, an iron oxide mineral that can form in water and that might indicate different conditions from the rocks above and below. Curiosity reached Vera Rubin Ridge in September 2017 and spent more than a year investigating it. The ridge lived up to expectations, showing distinctive mineralogy and evidence of complex alteration history. The rocks were harder and more resistant to erosion than the Murray Formation mudstones, which is why they formed a topographic high. They contained abundant hematite, giving them a reddish color, and also showed higher concentrations of silica than the rocks below. The high silica content was particularly intriguing. On Earth, concentrated silica can form in hot springs and other hydrothermal environments where silica-rich fluids circulate. The silica-rich zones on Vera Rubin Ridge might indicate that hydrothermal fluids flowed through these rocks at some point, potentially providing energy and nutrients that could have supported microbial life if it existed. After completing investigations on Vera Rubin Ridge, Curiosity continued ascending into what mission scientists called the clay-bearing unit. This unit had been identified from orbit as having strong clay mineral signatures, and reaching it had been a major objective since landing. Clays are key indicators of water activity and habitable conditions, so a unit rich in clays promised important insights into Martian habitability. Curiosity entered the clay-bearing unit in late 2018 and began intensive investigations in early 2019. The rocks here did indeed contain abundant clays, but interestingly, the clay minerals were different from those found at Yellowknife Bay. The composition and crystal structure variation suggested different formation conditions or different source rocks, adding complexity to the story of water activity in Gale Crater. The clay-bearing unit also showed extensive evidence of groundwater alteration. Many rocks contained nodules, concretions, and mineral veins indicating that water had circulated through them after deposition, dissolving some minerals and precipitating others. The extent of this alteration suggested that groundwater had been present for extended periods, possibly millions of years after the surface lake had dried up. As of early 2025, Curiosity had climbed more than 327 meters in elevation from the landing site, ascending through billions of years of Martian history recorded in the rock layers. The rover was exploring regions of Mount Sharp that represent increasingly young geological time, moving from the Hesperian period rocks at the base toward the Amazonian period rocks higher up. Each new geological unit Curiosity encounters adds detail to the story. The sulfate-bearing unit, which lies above the clay-bearing unit, has been a long-term target because sulfates indicate different water chemistry, likely more acidic and more evaporative conditions. The transition from clays to sulfates might mark the point when Mars's climate passed a threshold, becoming too cold and dry to sustain large bodies of surface water. The climb hasn't been without challenges. Mount Sharp slopes are steep in places, requiring careful route planning to ensure Curiosity doesn't get stuck or tip over. The rover's wheels have taken significant wear from sharp rocks, with holes punched through the aluminum treads. The mission team developed new driving techniques to minimize wheel damage, including driving backward in some situations and avoiding particularly rocky terrain even if it requires longer detours. There have also been instrument issues. The drill feed mechanism experienced problems in late 2016, preventing Curiosity from drilling for more than a year until engineers developed a workaround. The mast cam filter will showed some sticking behavior, requiring careful management to ensure continued functionality. Despite these challenges, the rover has remained remarkably capable, a testament to robust engineering and creative problem-solving by the mission team. The scientific return from the climb up Mount Sharp has been immense. Dozens of papers have been published analyzing the data from various drilling campaigns and outcrop investigations. The work has refined our understanding of Martian climate history, provided detailed characterization of ancient habitable environments, demonstrated that organic molecules are preserved in Martian rocks, and revealed the complexity of water activity on ancient Mars. One of the most significant findings has been the evidence for long-lived, stable habitable conditions. The thickness of the Murray Formation and the consistency of its mineralogy indicate that the lake environment in Gale Crater persisted for millions of years, not just brief wet episodes between long dry periods. This temporal stability is crucial for habitability because life needs time to emerge and establish itself. The methane mystery is one of the most intriguing and controversial aspects of Curiosity's mission. Methane is a simple organic molecule, one carbon atom bonded to 4 hydrogen atoms, and its presence on Mars has profound implications because it could potentially indicate biological activity. On Earth, most atmospheric methane is produced by living organisms, either directly through microbial metabolism or indirectly through the decomposition of organic matter. There are also non-biological sources like volcanic activity and geothermal processes, but biology is the dominant source on our planet. Mars's atmosphere is very thin and composed mostly of carbon dioxide. Methane, if present, would be a trace gas measured in parts per billion. What makes methane particularly interesting is its short lifetime in the Martian atmosphere. Ultraviolet radiation from the Sun breaks down methane molecules over a few hundred years, which is very short on geological time scales. This means that if methane is present in Mars's atmosphere today, something must be actively producing it. The methane isn't a remnant from billions of years ago. It's recent. Curiosity's SAM instrument began measuring atmospheric composition shortly after landing, and from the beginning, the methane results were puzzling. Some measurements detected no methane at all, or concentration so low they were at the limit of detection. Other measurements, seemingly randomly, detected significantly higher concentrations, sometimes 10 times higher than the background level. In June 2013, about a year after landing, SAM detected a methane spike, with levels reaching about 6 to 7 parts per billion, significantly higher than the less than 1 part per billion typically measured. The spike lasted for weeks and then declined back to background levels. The science team was cautious about announcing the result, spending months verifying the measurements and ruling out potential contamination or instrumental artifacts. When they did publish the finding in late 2014, it sparked intense interest and debate. Further measurements over subsequent years revealed a pattern. There appeared to be a seasonal cycle to methane concentrations, with higher levels during late summer and fall and lower levels during winter and spring. The variation was about 30%, not huge but statistically significant. This seasonal pattern suggested that whatever was producing or releasing the methane was influenced by Mars's seasons, perhaps responding to temperature changes or other seasonal factors. But there were also short-term spikes that didn't fit the seasonal pattern. In June 2019, Curiosity measured the highest methane concentration of the mission, about 21 parts per billion, 3 times higher than any previous measurement. This spike appeared suddenly and disappeared just as quickly, lasting only a day or two. Such rapid changes suggested localized releases, methane burping up from underground sources and then quickly dispersed by winds. The mystery deepened when the European Space Agency's ExoMars Trace Gas Orbiter, which arrived at Mars in 2016, began making its own measurements. This orbiter carries instruments designed specifically to detect trace gases in the Martian atmosphere with extreme sensitivity. The expectation was that it would confirm Curiosity's methane detections and perhaps identify where the methane was coming from by mapping its distribution across the planet. Instead, the Trace Gas Orbiter found essentially no methane. Its measurements, taken from orbit with high sensitivity, consistently showed methane concentrations below its detection limit of about 0.05 parts per billion. This directly contradicted Curiosity's ground-based measurements, creating a scientific controversy. How could Curiosity be detecting methane while an orbiter with even more sensitive instruments found none? Various explanations have been proposed. Perhaps the methane releases are highly localized and occur in plumes that disperse quickly, so they're only detectable near the source but not from orbit. Perhaps Curiosity is sampling right at ground level where methane might accumulate in calm air, while the orbiter is measuring the well-mixed atmosphere higher up. Perhaps there are diurnal variations, with methane concentrations higher at certain times of day that Curiosity measures but the orbiter doesn't. More controversial possibilities have also been raised. Could there be an instrumental artifact in Curiosity's measurements, something contaminating the samples or creating a false signal? Could there be terrestrial contamination, methane from Earth that hitched a ride on the spacecraft despite careful cleaning and sterilization? These possibilities seem unlikely given the thoroughness of the mission team's validation efforts, but they can't be entirely ruled out without independent confirmation. The sources of Martian methane, if it's truly present, are also debated. Biological production is one possibility. On Earth, methanogens are microorganisms that produce methane as a metabolic byproduct, thriving in oxygen-free environments like swamps and the digestive systems of animals. If microbial life exists in the Martian subsurface, in groundwater or wet soil, it might produce methane that seeps to the surface and is detected by Curiosity. But there are also numerous non-biological ways to produce methane. Water reacting with certain types of rocks at high temperatures can produce methane through a process called serpentinization. This occurs on Earth at mid-ocean ridges and in other geothermal settings. Mars might have subsurface geothermal heat from radioactive decay, and if water is present, similar reactions could produce methane. Another possibility is that methane is being released from ancient reserves trapped underground. Methane molecules could be locked in structures called clathrates, ice-like cages where methane molecules are physically trapped within a lattice of water molecules. These clathrates are stable at low temperatures and high pressures. If Mars has subsurface ice containing methane clathrates, seasonal warming could destabilize the clathrates, releasing methane gas that percolates to the surface. This could explain the seasonal pattern Curiosity observed. Ultraviolet radiation acting on organic-rich dust could also produce methane. Mars's surface contains organic molecules delivered by meteorites, and when these are exposed to intense UV radiation, they can break down into simpler molecules including methane. This process would produce methane continuously across the planet, though at low rates. Distinguishing between these possibilities requires more data. Measuring the carbon isotope ratio of the methane could provide clues, because biological and geological processes tend to prefer different carbon isotopes. Mapping where methane emissions occur could indicate whether they're coming from specific geological features like faults or volcanic regions. Measuring the methane concentration with multiple instruments simultaneously could help resolve the discrepancy between Curiosity's detections and the trace gas orbiter's non-detections. The methane mystery illustrates both the excitement and the frustration of Mars exploration. A potentially groundbreaking finding, methane that could indicate life, but with enough ambiguity and conflicting data that firm conclusions remain elusive. This is often how science works at the cutting edge. Clear-cut answers are rare. More often, you get tantalizing hints and puzzling contradictions that require more investigation to resolve. Regardless of the source, the possible presence of methane and the confirmed presence of other organic molecules shows that Mars has an active carbon chemistry. Carbon isn't locked away in carbonates or carbon dioxide. It's cycling between rocks, atmosphere, and potentially biological or geological processes that produce organic compounds. This dynamic carbon chemistry makes Mars more interesting from an astrobiology perspective than if it were a dead world with no organic chemistry at all. Curiosity's legacy extends far beyond the scientific papers and headlines. The mission has fundamentally changed how we think about Mars, transforming it from a dead, unchanging world into a planet with a complex and dynamic past, and perhaps even an active present. The rover has shown that Mars was once habitable, that it had environments where life could have emerged and thrived if the right circumstances came together. That knowledge reshapes the entire endeavor of Mars exploration. Before Curiosity, there was debate about whether Mars had ever truly been hospitable to life. Some scientists argued that Mars had been too cold, too dry, too hostile, and that the apparent water-carved features might have formed through unusual processes that didn't require stable liquid water. Curiosity definitively settled this debate. Mars had liquid water. It had lakes that persisted for millions of years. It had neutral pH water rich in minerals needed for life. It had organic carbon. The environments were habitable by any reasonable definition. This confirmation changes the goals of future missions. Instead of asking whether Mars could have supported life, we now ask whether life actually emerged. This is a more focused question, and answering it requires looking for specific biosignatures, evidence that can only be explained by biological processes. Such evidence might include particular types of organic molecules that are primarily produced biologically, or rock structures that resemble microbial fossils, or patterns in isotopic ratios that indicate biological fractionation. The Perseverance rover, exploring Gale Crater since 2021, is specifically designed to search for these biosignatures. It carries instruments that can detect and analyze organic molecules with even greater sensitivity than Curiosity's instruments. It's exploring an ancient river delta where conditions for preserving biosignatures might be optimal. And critically, it's collecting samples that will eventually be returned to Earth for analysis in laboratories with capabilities far beyond anything that can be sent to Mars. This Mars Sample Return Campaign, a collaboration between NASA and the European Space Agency, is the logical next step enabled by Curiosity's discoveries. The samples Perseverance is collecting include rocks from environments identified as habitable, similar to the environments Curiosity explored. When these samples reach Earth, likely in the early 2030s if the mission proceeds as planned, scientists will subject them to the most sophisticated analyses ever applied to Martian materials. If biosignatures exist and were preserved, the sample return mission offers the best chance of finding them. Curiosity also paved the way technologically. The Sky Crane landing system that seemed so risky when Curiosity used it has now been proven twice, with Perseverance using an improved version of the same system to land successfully in Gale Crater. Future missions will continue using this capability to land large payloads in challenging terrain, opening up more of Mars to exploration. The mission demonstrated that a rover can operate for more than a decade in Mars's harsh environment, far exceeding its design lifetime. This longevity was enabled by the radioisotope power source, which will continue to provide power for potentially decades more, and by robust engineering that anticipated wear and degradation. Future rover missions are incorporating these lessons, using similar power systems and designing for long operational lifetimes. Curiosity also serves as a testbed for technologies that will be essential for human exploration. The radiation measurements from RAD have quantified the exposure astronauts will face, informing the design of spacecraft shielding and surface habitats. The environmental monitoring has characterized temperature extremes, dust storm frequency, and other conditions that human missions must prepare for. The demonstration that water-bearing minerals are widespread provides potential resources that could be used to produce water for astronauts or to manufacture rocket fuel for the return journey. The mission's scientific legacy is still being written. Data from Curiosity continues to be analyzed, with new papers published regularly as scientists dig deeper into the measurements and as new analytical techniques become available. The full stratigraphic section that Curiosity is ascending will take years more to complete, with each new layer adding detail to the climate history. The methane mystery remains unsolved, awaiting more data from Curiosity, from orbiters, and from future surface missions. Curiosity has also inspired public interest in Mars exploration. The rover's landing was watched by millions, and its ongoing adventures are followed by space enthusiasts around the world. The dramatic landscapes it photographs, the intriguing science it performs, and even its quirky personality on social media have made it a cultural icon. This public engagement is crucial because it builds support for continued exploration and for the substantial funding required for missions like Curiosity. Looking ahead, the exploration of Mars will accelerate. Multiple missions are planned or under consideration for the next 2 decades. NASA's Mars sample return will bring back rocks collected by Perseverance. The Dragonfly mission, though going to Saturn's moon Titan rather than Mars, will use technologies pioneered on rovers like Curiosity. International missions from China, India, and the United Arab Emirates are adding to the growing armada of spacecraft studying Mars. And human missions, perhaps in the late 2030s or 2040s, will represent the ultimate expression of our drive to explore. When humans finally reach Mars, they'll walk on ground that Curiosity helped us understand. They'll see landscapes that the rover photographed, touch rocks that it analyzed, and build on the scientific foundation that it established. They'll search for life in environments that Curiosity identified as habitable. They'll follow in the tracks, literal and figurative, that Curiosity laid down. The rover itself, when it finally stops functioning, will remain on Mars as a monument to human curiosity and ingenuity. Unlike missions to the moon where astronauts could retrieve equipment, nothing will be brought back from Mars for decades at least. Curiosity will stay in Gale Crater, a technological artifact alongside the geological features it studied. Future explorers might visit it, examining how it weathered and degraded, using it to calibrate their understanding of how materials behave in the Martian environment. But that's far in the future. For now, Curiosity continues its mission, climbing Mount Sharp, analyzing rocks, and sending back data. Every day it operates is a bonus, extending what was already an extraordinarily successful mission. The rover might last another decade or more, or a critical component might fail tomorrow. Either way, its place in the history of Mars exploration is secure. The story of Curiosity is ultimately a story about persistence and patience. Persistence in the decades-long effort to get the mission approved, funded, designed, built, and launched. Persistence in overcoming technical challenges during development and operation. Persistence in the rover itself, which has outlasted all expectations and continues to function in one of the harshest environments imaginable. And patience in the scientific process, the careful accumulation of evidence, the rigorous analysis, the peer review and debate that turns observations into understanding. There are no quick answers in planetary science. Every conclusion is built on thousands of measurements, multiple lines of evidence, comparison to terrestrial analogues, and extensive modeling. The work is painstaking and slow, but it produces knowledge that transforms our understanding of the universe. If you've been with us through this journey into Gale Crater, through billions of years of Martian history, through the discoveries and mysteries that Curiosity has revealed, you've glimpsed the wonder of scientific exploration. You've seen how a robot on another world, controlled by humans millions of kilometers away, can read stories written in stone and answer profound questions about the history of a planet and the possibilities for life beyond Earth. Mars no longer seems quite so alien after spending time with Curiosity. It's a place with history, with geology shaped by familiar processes like water and wind and time. It's a world that was once habitable, that might still hold surprises in its soil or ice. It's a destination, somewhere that humans will eventually walk, extending the chain of exploration that Curiosity represents. As you drift off, think about that lonely robot on its mountainside, under a butterscotch sky, surrounded by rocks billions of years old. Think about the team of scientists and engineers who wake up every day to explore Mars through Curiosity's eyes. Think about the questions still unanswered and the discoveries still waiting to be made. The path forward for Mars exploration builds directly on what Curiosity has accomplished. Every mission proposal, every landing site selection, every instrument design is informed by the knowledge Curiosity has provided. The rover showed us where to look, what to look for, and how to interpret what we find. It demonstrated that ancient Mars was habitable, but it also revealed how complex that habitability was, with changing conditions, diverse environments, and a gradual transition to the harsh world we see today. Future missions will drill deeper than Curiosity could, accessing rocks from further underground where preservation of biosignatures might be better. They'll carry more sophisticated organic chemistry instruments, capable of distinguishing between biological and non-biological organic molecules based on their structure and composition. They'll have improved imaging systems that can photograph rock textures at even finer scales, looking for microscopic structures that might be microfossils. The search for life on Mars is entering a new phase, moving from establishing habitability to actively hunting for biosignatures. This is thanks largely to Curiosity proving that Mars offered opportunities for life to emerge. We now know what kind of environments to target: ancient lake beds with neutral pH water, regions with clay minerals formed by prolonged water exposure, areas where groundwater circulated and might have provided energy for subsurface ecosystems. But the search isn't limited to ancient life. The methane detections, controversial as they are, raise the possibility of current biological or geological activity. If methane is truly being produced on Mars today, finding the source becomes a priority. Is it ancient methane trapped in ice and slowly leaking out? Is it being produced by active geothermal processes? Or, most intriguingly, could it be produced by microorganisms clinging to existence in subsurface aquifers or damp soil? These questions drive mission concepts for the next decade. A geophysical network of seismometers and heat flow probes could map Mars's interior structure and identify geologically active regions. Subsurface drilling missions could access groundwater or ice deposits where present-day life might exist. Aerial vehicles, drones or balloons, could survey large areas looking for active methane seeps or other signs of current activity. The technology demonstrated by Curiosity and Perseverance is also being adapted for exploring other worlds. The Mars rover design has influenced concepts for Venus rovers that could withstand that planet's hellish surface conditions. The instruments developed for analyzing Martian samples are being adapted for missions to the icy moons of Jupiter and Saturn, where subsurface oceans might harbor life. The lessons learned about autonomous navigation and long-duration operation in hostile environments apply to missions throughout the solar system and beyond. Curiosity's impact extends beyond planetary science into broader questions about the nature and distribution of life in the universe. The discovery that Mars was habitable has implications for the habitability of planets around other stars. If 2 out of 3 terrestrial planets in our solar system had habitable surface conditions at some point, even though only one retained them, it suggests that habitability might be common. The universe might be full of planets that are habitable for periods of their history, even if they don't remain so indefinitely. This has philosophical implications too. If life emerged on both Earth and Mars independently, it would suggest that life arises readily whenever conditions permit. The universe would likely be teeming with life, at least microbial life, on countless worlds. But if Mars was habitable yet lifeless, it would suggest that the emergence of life is rare even when conditions seem favorable, and we might be more alone than we'd hoped. These profound questions can only be answered through continued exploration. We need to search more of Mars, examining different types of ancient environments to see if we can find biosignatures anywhere. We need to explore the Martian subsurface, looking for present-day habitable niches. We need to bring samples back to Earth for definitive analysis. And eventually, we need human explorers with the intelligence and flexibility to investigate in ways that robots simply cannot. The timeline for human Mars exploration remains uncertain, but the goal is becoming more achievable. Multiple nations and even private companies are developing the technologies required for human Mars missions. Heavy-lift rockets capable of launching the massive payloads needed are being tested. Life support systems that can recycle air and water for years are being refined on the International Space Station. Spacesuits designed for extended exploration on planetary surfaces are in development. When humans finally walk on Mars, perhaps in the 2035 to 2040 timeframe, they'll face challenges that Curiosity never had to worry about. They'll need food, water, and air. They'll need protection from radiation during the months-long journey and on the surface. They'll need shelter capable of withstanding dust storms and temperature extremes. They'll need reliable equipment because a breakdown that Curiosity's team could work around for months might be life-threatening for astronauts. But humans will also bring capabilities that no robot possesses. They'll be able to traverse kilometers in a day rather than meters. They'll recognize interesting features immediately rather than waiting hours for images to reach Earth and instructions to return. They'll make intuitive leaps and creative decisions that artificial intelligence can't match. They'll physically experience Mars in ways that remote sensing can never capture, feeling the gravity, seeing the colors with their own eyes, picking up rocks with their gloved hands. Those future explorers will undoubtedly visit Gale Crater. Standing where Curiosity landed, looking toward Mount Sharp, they'll see a landscape made familiar by the rover's tireless exploration. They might climb higher up Mount Sharp than Curiosity could reach, accessing even younger geological units that record Mars's transition into its current frozen state. They might drill deep into the mountain's flanks, extracting long cores that can be analyzed on the surface or returned to Earth. They'll also honor Curiosity itself, the pioneering robot that blazed the trail they are following. Perhaps they'll take close-up photographs of the rover, documenting how it weathered Mars's environment. Perhaps they'll even attempt repairs, giving Curiosity a second life under human stewardship. Or perhaps they'll simply stand in its presence, acknowledging the achievement it represents and the knowledge it unlocked. The story of Curiosity is far from over. The rover continues operating, continues climbing, continues discovering. Every additional day of operation is a gift, providing more data and more insights. The mission might continue for years more, or it might end tomorrow. Either way, what Curiosity has accomplished will resonate through Mars exploration for generations. In a sense, every human who eventually walks on Mars will be standing on the shoulders of robots like Curiosity. The knowledge those robots gained, the maps they made, the hazards they identified, and the discoveries they achieved are the foundation for human exploration. Robots and humans aren't competing in space exploration. They're partners, with robots going first to scout the way and humans following to push the boundaries further. This partnership between human ingenuity and robotic capability is one of the great achievements of space exploration. We build machines that can survive environments we cannot, equip them with instruments that extend our senses, and send them to places we dream of visiting. Through their electronic eyes, we see other worlds. Through their instruments, we touch alien rocks and taste alien air. Through their persistence, we extend our presence beyond our fragile planet into the cosmos. Curiosity embodies this partnership. It's a product of human creativity, designed and built by thousands of people over decades. But it's also an autonomous entity, making decisions on its own, navigating hazards, and adapting to circumstances that its creators never anticipated. It's both tool and explorer, an extension of human curiosity taking physical form and venturing where we cannot yet go. The rover's journey continues into the unknown. Higher up Mount Sharp, geological units await that have never been examined close-up. The sulfate-bearing unit, in particular, holds promise for understanding Mars's drying climate. Even higher, though beyond Curiosity's likely reach, are units that might record the final chapter of surface water activity, the moment when Mars's climate crossed a threshold and the planet became the frozen desert it is today. Every meter Curiosity climbs is a step further into that story. Every sample it drills adds a data point to the climate record. Every measurement contributes to humanity's understanding of how planets evolve and what determines whether they remain habitable. This isn't just about Mars. It's about understanding the broader processes that shape all rocky planets, including our own Earth. Climate change is a pressing concern on our planet, and understanding how Mars lost its habitable climate provides sobering context. Mars shows us that planetary climates aren't necessarily stable, that they can transition from life-friendly to hostile over geological time. While the mechanisms differ, Earth's warming atmosphere from human activities is our own experiment in rapid climate change. The lessons from Mars about atmospheric loss, greenhouse effects, and environmental transitions are more than academic. They're cautionary tales written in stone on another world. So as Curiosity continues its lonely vigil on Mount Sharp, analyzing rocks under an alien sky, it's doing more than exploring Mars. It's illuminating our understanding of planets in general, habitability and climate, the possibilities for life beyond Earth, and our own planet's precious and perhaps fragile habitability. The knowledge gained reverberates across multiple fields of science and informs how we think about our place in the universe. Sleep well, knowing that tonight, as every night, Curiosity sits on Mars. The butterscotch sky fades to black as the sun sets. The temperature plummets. The thin wind whispers across ancient rocks. And somewhere in that frozen landscape, a robot built by humans continues its mission. One drill hole, one laser zap, one photograph at a time, reading the history of a world and searching for answers to humanity's deepest questions. If you're enjoying this journey through space and time, let us know by liking this video, subscribing to the channel, and joining us for future explorations into the wonders of our universe. Until next time, rest well and dream of distant worlds where robots roam and secrets wait to be discovered.